Third stream. Yay. Okay. Audio's going. Everything's going. Let's check this. Boop. Turn that on. Ba, 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 ba. Okay. Yay! Yay. Let's continue. Okay. So we have a couple options here for what we can do. We can continue with this. We can start reading the manual. Um, we can fuck around with this. Actually, yeah, I think I'm gonna. Yes. Go for Windows. Okay. Sorry, no. Stable. Okay, I want this. I want Pixelrama. I don't exact I don't have the most recent version of Godot. So, most recent version. Yay. We'll just close that. Let's figure this out. Brown, 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 brown. And just move that right there. Alright, and launch. Alright, so, and anyway. It's just Godot, it's fine. Yeah. How do I get this? Oh, it's on Steam. Oh. Oh. Well, damn. I'm gonna wishlist that though. I'm gonna Ah, yeah, I'm gonna wishlist that. Pixel-O-Rama. To your wish list. Alright. Boop. Yeah, we can either do that or we can do this. This is an option that we can do to learn the GD script for Godot. Not feeling like it though. Could be feeling like it. Am I feeling like it? Second lesson. Oh Jesus, that's a lot of lessons. That's a that's a lot of lessons. We'll continue with this. I did label this episode 2, right? Oh shit, you guys. Whoops. Screen capture. Why are you on the wrong screen? There we go. Okay. Yay. Okay, so yeah, a lot of lessons. And then we could continue with this, or we can learn Godot's scripting language. Eh, eh. Hello? Just go back. Go, go back. Yeah, it's fine. All right, let's see. Introduction. This series is a collection of best practices to help you work efficiently with Godot. Godot allows for a great amount of dog. Okay, I know it wasn't great last time, but like want another one. I want one. I want gum. I like gum. Gum is nice. Mm. This series is a collection of best practices to help you work efficiently with Godot. Good. Godot allows for a great amount of flexibility in how you structure a project's codebase and break it down into scenes. Each approach has its pros and cons, and they can be hard to weigh until you've worked with the engine for long enough. There are always many ways to structure your code and solve specific programming problems. It would be impossible to cover them all here. That's why each article starts from a real-world problem. We will break down each problem in fundamental questions, suggest solutions, analyze the pros and cons of each option, and highlight the best course of action for the problem at hand. You should start by reading Applying Object-Oriented Principles in Godot. It explains how Godot's nodes and scenes relate to classes and objects in other object-oriented programming languages. It will help you make sense of the rest of the series. Note: best practices in Godot rely on object-oriented design principles. We use tools like single responsibility principle and encapsulation. Which do we got? A lot. Like so much. Applying object-oriented principles in Godot. The engine offers two main ways to create reusable object scripts and scenes. Neither of these technically define classes under the hood. Okay. Still, many best practices using Godot involve applying object-oriented programming principles to the scripts and scenes that compose your game. That is why it's useful to understand how we can think of them as classes. This guide briefly explains how scripts and scenes work in the engine's core to help you understand how they work under the hood. How scripts work in the engine. The engine provides built-in classes like node. You can extend those to create derived types using a script. These scripts are not technically classes. Instead, they are resources that tell the engine a sequence of initializations to perform one of the engine's built-in classes. Godot's internal classes have methods that register a class's data with a class DB. This database provides runtime access to class information. Class DB contains information about classes like properties, methods, constants, signals. This class DB is what objects check against when performing an operation like accessing a property or calling a method. It checks the database's records and the object's base types records to see if the object supports the operation. Attaching a script to your object extends the methods, properties, and signals available from the class DB. Note: even scripts that don't use the extends keyword implicitly inherit the engine's base ref-counted class. As a result, you can instantiate scripts without the extends keywords from code, since they extend ref-counted, though you cannot attach them to a node. The behavior of scenes has many similarities to classes, so it can make sense to think of a scene as a class. Scenes are reusable, instantiable, and inheritable groups of nodes. Creating a scene is similar to having a script that creates nodes and adds them as children using addChild. We often pair a scene with a scripted root node that makes use of the scene's nodes. As such, the script extends the scene by adding behavior through imperative code. The content of a scene helps to define what nodes are available to the script, how they are organized, how they are initialized, what signal connections they have with each other. Why is any of this important to scene organization? Because instances of scenes are objects. As a result, many object-oriented principles that apply to written code also apply to scenes, single responsibility encapsulation, and others. The scene is always an extension of the script attached to its root node, so you can interpret it as part of a class. Most of the techniques explained in the Best Practices series builds on this point. I was just looking at this and like, holy shit. I have to go through a lot of this. Because these are all sections and they all have their own subsections. I'm not going through 3D. because I'm not going to be making 3D games. If I do want to make a 3D game in the future, I'll just come back to the documentation. Scene organization. This article covers topics related to the effective organization of scene content. Which nodes should you use? Where should you place them? How should they interact? How to build relationships effectively. When Godot users begin crafting their own scenes, they often run into the following problem. They create their first scene and fill it in with content Blech. They create their first scene and fill it with content only to eventually end up saving branches of their scene into separate scenes as the nagging feeling that they should split things up starts to accumulate. However, they then notice that the hard references they were able to rely on before are no longer possible. Reusing the scene in multiple places creates issues because the node paths do not find their targets and signal connections established in the editor break. To fix these problems, you must instantiate the subscenes without them requiring details about their environment. You need to be able to trust that the subscene will create itself without being picky about how it's used. One of the biggest things to consider in OOP is maintaining focused, singular-purpose classes with loose coupling to other parts of the codebase. This keeps the size of objects small for maintainability and improves their reusability. These OOP best practices have several implications for best practices in scene structure and script usage. If at all possible, you should design scenes to have no dependencies. That is, you should create scenes that keep everything you need within themselves. If a scene must interact with an external context, experienced developers recommend the use of dependency injection. This technique involves having a high-level API provide the dependencies of the low-level API. Why do this? Because classes which rely on their external environment can inadvertently trigger bugs and unexpected behavior. To do this, you must expose data and then rely on a parent context to initialize it. Connect to a signal extremely safe but should be used only to respond to behavior, not start it. By convention, signal names are usually past tense verbs like entered, skill activated, or item collected. Call method used to start behavior. Initialize a callable property, safer than a method as ownership of a method is unnecessary. Used to start behavior. Initialize a node or other object reference. Initialize node path. Use option hide the points of access from the child node. This in turn keeps a child loosely coupled to its environment. You can reuse it in another context without any extra changes to its API. Although the examples above illustrate parent-child relationships, the same principles apply towards all object relations. Nodes which are siblings should only be aware of their own hierarchies, while an ancestor mediates their communications and references. The same principles also apply to non-node objects that maintain dependencies on other objects. Whichever object owns the other object should manage the relationships between them. Warning, you should favor keeping data in-house internal to a scene, though as placing a dependency on an external context, even a loosely coupled one, still means that the node will expect something in its environment to be true. The project's design philosophy should prevent this from happening. If not, the code's inherent liabilities will force developers to use documentation to keep track of object relations on a microscopic scale. This is otherwise known as development hell. Writing code that relies on external documentation to use it safely is error-prone by default. To avoid creating and maintaining such documentation, you convert the dependent node, child above, into a tool script that implements get configuration warnings. Returning a non-empty package string array from it will make the scene doc generate a warning icon with the strings as a tooltip by the node. This is the same icon that appears for nodes such as the Area 2D node when it has no child collision shape 2D nodes defined. The editor then self-documents the scene through the script code. No content duplication via documentation is necessary. A GUI like this can better inform project users of critical information about a node. Does it have external dependencies? Have those dependencies been satisfied? Other programmers, and especially designers and writers, will need clear instructions in the messages telling them what to do to configure it. So why does all this complex switcheroo work? Well, because scenes operate best when they operate alone, if unable to work alone, then working with others anonymously with minimal hard dependencies, i.e. loose coupling, is the next best thing. Inevitably, changes may need to be made to a class, and if these changes cause it to interact with other scenes in unforeseen ways, then things will start to break down. The whole point of this indirection is to avoid ending up in a situation where changing one class results in adversely affecting other classes dependent on it. Scripts and scenes, as extensions of engine classes that should abide by all OOP principles. Examples include solid, dry, kiss, yagni. Choosing okay. Choosing a node tree structure. You might start to work on a game but get overwhelmed by the vast possibilities before you. You might know what you want to do, what systems you want to have, but where do you put them all? How do you go about making your game is ugh, how do you go about making your game is always up to you. You can construct node trees in countless ways. If you are unsure, this guide can give you a sample of a decent structure to start with. A game should always have an entry point, somewhere you can definitively track where things begin so that you can follow the game logic as it continues elsewhere. It also serves as a bird's eye view of all other data and logic in the program. For additional applications, this is normally a main function. In Godot, it's a main node main.gd. The main GD script will serve as the primary controller of your game. Then you have an in-game world, a 2D or 3D one. This can be a child of main. In addition, you will need a primary GUI for your game that manages the various menus and widgets the project needs. Node main.gd. Node 3D, no, 2D, 3D, world, gameworld.gd, control GUI, GUID. When changing levels, you can swap out the children of the world node. Changing scenes manually gives you full control over how your game world transitions. The next step is to consider what gameplay systems your project requires. If you have a system that tracks all of its data internally, should be globally accessible, should exist in isolation, then you should create an autoload singleton node. For smaller games, a simpler alternative with less control would be to have a game singleton that simply calls the scene tree change scene to file method to swap out the main scene's content. The structure more or less keeps the world as the main game node. Any GUI would also need to be either a singleton, a transitory part of the world, or manually added as a direct child of the root. Otherwise, the GUI nodes would also delete themselves during scene transitions. If you have systems that modify other systems' data, you should define those as their own scripts or scenes, rather than autoloads. For more information, see autoloads versus regular nodes. Each subsystem within your game should have its own section within the scene tree. You should use parent-child relationships only in cases where nodes are effectively effectively elements of their parents. Does removing the parent reasonably mean that the children should also be removed? If not, then it should have its own place in the hierarchy as a sibling or some other relation. Taking Bella for a walk? Ah, fun. In note, in some cases you need these separated nodes to also position themselves relative to each other. You can use the remote transform or remote transform 2D nodes for this purpose. They will allow a target node to conditionally inherit selected transform elements from the remote node to assign the target node path. Use one of the following: a reliable third party, likely a parent node, to mediate the assignment, a group to pull a reference to the desired node, assuming there will only ever be one of the targets. When you should do this When should you do this subjective? This is subjective. The dilemma arises when you must micromanage when a node must move around the scene to preserve itself. For example, add a player node to a room. Need to change rooms, so you must delete the current room. Before the room can be deleted, you must preserve and or remove the player. If memory is not a concern, you can create the new room, move the player to the new room, delete the old room. If memory is a concern, instead you'll need to move the player somewhere else in the tree, delete the room, instantiate and add the new room, re-add the player to the new room. The issue is that the player here is a special case where the developers must know that they need to handle the player this way for the project. The only way to reliably share this information as a team is to document it. Keeping implementation details in documentation is dangerous. It's a maintenance burden, strains code readability, and unnecessarily bloats the intellectual content of a project. In a more complex game with larger assets, it can be a better idea to keep the player somewhere else in the scene tree entirely. This results in more consistency, no special cases that must be documented and maintained elsewhere, no opportunity for errors to occur because these details are not accounted for. In contrast, if you ever need a child node that does not inherit the transform of its parent, you have the following options. The declarative solution, place a node in between them. Since it doesn't have a transform, they won't pass this information to its child. The imperative solution, use the top level property for the canvas item or node 3D node. This will make the node ignore its inherited transform. Note, if building a network... Second note. If building a networked game, keep in mind which nodes and gameplay systems are relevant to all players, versus those just pertinent to the authoritative server. For example, users do not all need to have a copy of every player's player control logic. They only need their own. Keeping them in a separate branch from the world can help simplify the management of game connections and the like. Hello, Shelby. The key to scene organization is to consider the scene tree in relational terms rather than spatial terms. Are the nodes dependent on their parent's existence? If not, they can thrive all by themselves somewhere else. If they are dependent, then it stands to reason that they should be children of that parent, and likely part of that parent's scene if they aren't already. Does this mean nodes themselves are components? Not at all. Godot's node trees form an aggregation relationship, not one of composition, but while you still have the flexibility to move nodes around, it is still best when such moves are unnecessary by default. Adderall. Water. Ah. Okay. When to use scenes versus scripts. We've already covered how scenes and scripts are different. Scripts define an engine class extension with imperative code. Scenes with declarative code. Each system's capabilities are different as a result. Scenes can define how an extended class initializes, but not what its behavior actually is. Scenes are often used in conjunction with a script, the scene declaring a composition of nodes and the script adding behavior with imperative code. It is possible to completely define a scene's contents using a script alone. This is, in essence, what the Godot editor does, only in the C++ constructor of its objects, but choosing which one to use can be a dilemma. Creating a script instances is identical to creating in-engine classes, whereas handling scenes requires a change in API. Also, scripts will operate a little slower than scenes due to the speed differences between engine and script code. The larger and more complex a node, the more reasons there is to build it as a scene. Name types. Scripts can be registered as a new type within the editor itself. This displays it as a new type in the node or resource creation dialog with an optional icon. This way, the user's ability to use the script is much more streamlined rather than having to 1. Know the base type of the script they would like to use, 2. Create an instance of that base type, 3. Add the script to the node. With a registered script, the scripted type instead becomes a creation option, like the other nodes and resources in the system. The creation dialog even has a search bar to look up the type by name. There are two systems for registering types. Custom types, editor-only type names, are not accessible at runtime. Does not support inherited custom types. An initializer tool creates a node with the script, nothing more. Editor has no type awareness of the script or its relationship to other engine types or scripts. Allows users to define an icon. Works for all scripting languages because it deals with script resources in abstract. Set up using editor plugin.add custom type. Script classes, editor and runtime accessible, disable, displays inheritance relationships in full. Creates a node with the script, but can also change types or extend the type from the editor. Editor is aware of inheritance relationships between scripts, script classes, and Engine C++ classes. Allows users to define an icon. Engine developers must add support for languages manually, both name, exposure, and runtime accessibility. The editor scans project folders and registers any exposed names for all scripting languages. Each scripting language must implement its own support for exposing this information. Both methodologies add names to the creation dialog, but script classes in particular also allow for both users to access the type name without loading the script resource. Creating instances and accessing constants or static methods is viable from anywhere. With features like these, one may wish their type to be a script without a scene due to its ease of use. It grants users. Those developing plugins or creating in-house tools for designers to use will find an easier time of things this way. On the downside, it also means having to use largely imperative programming, performance of script versus packed scene. One last aspect to consider when choosing scenes and scripts in execution speed. As the size of objects increases, the script's necessary size to create and instantialize them grows much larger. Creating node hierarchies demonstrates this. Each node's logic could be several hundred lines of code in length. The code example below creates a new node, changes its name, assigns a script to it, sets its future parent as its owner so it gets saved to disk along with it, and finally adds it as a child of the main node. God damn it. Where'd it go? What? Huh? I dropped the bouncy ball that I had. That was just tossing around. And it just slipped into the back rooms. What? Found it. Yay. Okay, where was I? Comfrey. Performance of script versus packed scene. One last aspect. Knocking my headphones all around. One last aspect to consider when choosing scenes and scripts is execution speed. As the size of objects increases, the script's necessary size to create and initialize them grows much larger. Creating node hierarchies demonstrates this. Each node's logic could be several hundred lines of code in length. The code examples below create a new node. A new node changes its name, assigns a script to it, sets its future parent as its owner so it gets to get saved to disk along with it, and finally adds it as a child of the main node. Script code like this is much slower than engine-side C++ code. Each instruction makes a call to the scripting API, which leads to many lookups on the back end to find the logic to execute. Scenes help to avoid this performance issue. Packed scene, the base type that scenes inherit from, defines resources that use serialized data to create objects. The engine can process scenes in batches on the back end and provide much better performance than scripts. Conclusion. In the end, the best approach to consider is the following. If one wishes to create a basic tool that is going to be reused in several different projects and which people of all skill levels will likely use, including those who don't label themselves as programmers, then chances are that it should probably be a script, likely one with a custom name or icon. if one wishes to create a concept that is particular to their game, then it should always be a scene. Scenes are easier to track / edit and provide more security than scripts. If one would like to give a name to a scene, then they can still sort of do this by declaring a script class and giving it a scene as a constant. The script becomes, in effect, a namespace. What is this? This one isn't that long. Autoloads versus regular nodes. Godot offers a feature to automatically load nodes at the root of your project, allowing you to access them globally. That can fulfill the role of a singleton's autoload. These autoloaded nodes are not freed when you change the scene from code with scene tree change scene to file. In this guide, you will learn how to use the autoload feature and techniques you can use to avoid it. The cutting audio issue. Other engines can encourage the use of creating manager classes, singletons that organize a lot of functionality into a globally accessible object. Godot offers many ways to avoid global state thanks to the node tree and signals. Shelby. Doggo. Shelby. Cutting audio issue. Other engines can encourage the use of creating manager classes, singletons that organize a lot of functionality into a globally accessible object. Godot offers many ways to avoid global state thanks to the node and tree signals. I just read that. For example, let's say we are building a platformer and want to collect coins that play a sound effect. There's a node for that, the audio stream player, but if we call the audio stream player while it is already playing a sound, the new sound interprets the first. A solution is to code a global autoloaded sound manager class. It generates a pool of audio stream player nodes that cycle through as each new request for sound effects comes in. Say we call that class sound. You can use it from anywhere in your object by calling soundplay coinpickup.ogg. This solves the problem in the short term but causes more problems. Global state. One object is now responsible for all objects' data. If the sound class has errors or doesn't have an audio stream player available, all the nodes calling it can break. Global access. Now that any object can call sound.play soundpath from anywhere, there's no longer an easy way to find the source of the bug. Global resource allocation. With a pool of audio stream player nodes stored from the start, you can... Shelby! No need for barking. Where was I? Sound effect, there's an audio streamer, but if we call the audio streamer while it is already playing, the sound interrupts it first. A solution is to code a global autoloaded sound manager class that generates a pool of audio stream player nodes that cycle through as each new request for sound effects comes in. Say we call that class sound, you can use it from anywhere in your project by calling sound.play. This solves the problem in the short term but causes more problems. Hey! You're okay. You're fine. There's no need for that. A solution is to global state. One object is now responsible for all objects' data. If the sound class has errors or doesn't have an audio stream player available, all the nodes calling it can break. Global access. Now that any object can call sound play sound path from anywhere, there's no longer an easy way to find the source of the bug. Global resource allocation. With a pool of audio stream player nodes stored from the start, you can either have too few and face bugs, or too many and use more memory than you need. Go on. Note about global access. The problem is that any code anywhere could pass wrong data to the sound autoload in our example. As a result, the domain to explore to fix the bug spans the entire project. When you keep code inside a scene, only one or two scripts may be involved in audio. Contrast this with with each scene keeping as many audio stream player nodes as it needs within itself, and all these problems go away. Each scene manages its own state information. If there is a problem with the data, it will only cause issues in that one scene. Each scene accesses only its own nodes. If there is a bug, it's easy to find which node is at fault. Each scene allocates exactly the amount of resources it needs. Managing shared functionality or data. Another reason to use an autoload can be that you want to reuse the same method or data across many scenes. In the case of functions, you can create a new type of node that provides that feature for an individual scene using the class name keyword in GDScript. When it comes to data, you can either 1. Create a new type of resource to share the data. 2. Store the data in an object to which each node has access, for example, using the owner property to access the scene's root node. Bleh. When should you use an autoload? GDScript supports the creation of static functions using static function. When combined with class name, this makes it possible to create libraries of helper functions without having to create an instance to call them. The limitation of static functions is that they can't reference member variables, non-static functions, or self. Since Godot 4.1, GDScript also supports static variables using static variable. This means you can now share variables across instances of a class without having to create a separate autoload. Still, autoload nodes can simplify your code for systems with a wide scope. If the autoload is managing its own information and not invading the data of other objects, then it's a great way to create systems that handle broad scope tasks, for example, a quest or dialogue system. Note, an autoload is not necessarily a singleton. Nothing prevents you from instantiating copies of an autoloaded node. An autoload is only a tool that makes a node load automatically as a child of the root of your scene tree, regardless of your game's node structure or which scene you run, e.g. by pressing the F6 key. As a result, you can get the autoloaded node. For example, an autoload called sound by calling getNode root sound. Blah. Blah, blah, blah. Blah, blah, blah. A lot of reading. Water. When and how to avoid using nodes for everything. Nodes are cheap to produce, but even they have their limits. A project may have tens of thousands of nodes all doing things. The more complex their behavior, though, the larger the strain each one adds to the project's performance. Godot provides more lightweight objects for creating APIs, which nodes use. To be sure to keep these in mind as options when designing how you wish to build your project's features. Object, the ultimate lightweight object. The original object must use manual memory management. With that said, it isn't too difficult to create one's own custom data structures, even node structures that are also lighter than the node class. Example, see the tree node, it supports a high level of customization for a table of content with an arbitrary number of rows and columns. The data that it uses to generate its visualization though is actually a tree of tree item objects. Advantages: simplifying one's API to smaller scoped objects helps improve its accessibility and improve iteration time. Rather than working with the entire node library, one creates an abbreviated set of objects from which a node can generate and manage the appropriate subnodes. Note: one should be careful when handling them. One can store an object into a variable, but these references can become invalid without warning. For example, if the object's creator decides to delete it out of nowhere, this would trigger an error state when one next accesses it. Ref counted. Only a little more complex than object, they track references to themselves, only deleting loaded memory when no further references to themselves exist. These are useful in the majority of cases where one needs data in a custom class. Example, see the file access object. It functions just like a regular object, except that one need not delete it themselves. Advantages, same as the object. 3. Resource. Only slightly more complex than ref counted. They have the innate ability to serialize, deserialize, i.e. save and load their object properties to and from Godot resource files. Example, scripts packed scene for scene files, and other types like each of the audio effect classes. Each of these can be saved and loaded, therefore they extend from resource. Advantages. Much has already been said on resources advantages over traditional data storage methods. In the context of using resources over nodes though, their main advantage is in inspector compatibility. While nearly as lightweight as object ref counted, they can still display and export properties in the inspector. This allows them to fulfill a purpose much like subnodes on the usability front, but also improve performance if one plans to have many such resources/nodes in their scene. Godot interfaces. Often one needs scripts that rely on other objects or features. There are two parts of this process. One, acquiring a reference to the object that presumably has the features. Two, accessing the data or logic from the object. The rest of this tutorial outlines the various ways of doing all this. Acquiring object references. For all objects, the most basic way of referencing them is to get a reference to an existing object from another acquired instance. Okay. Alright. The same principle applies for ref-counted objects. While users often access node and resources this way, alternative measures are available. Instead of property or method access, one can get resources by load access. That's a lot. Note the following. There are many ways in which language can load such resources. When deciding how objects will access data, don't forget that one can pass resources around as references as well. Keep in mind that loading a resource fetches the cached resource instance maintained by the engine. To get a new object, one must duplicate an existing reference or instantiate one from scratch with new. Nodes likewise have an alternative access point, the scene tree. Accessing data or logic from an object. Godot scripting API is duck-typed. This means that if a script executes an operation, Godot doesn't validate that it supports the operation by type. It instead checks that the object implements the individual method. For example, the canvas item class has a visible property. All properties exposed to the scripting API are in fact setter and getter pair bound to a name. If one tried to access canvas item visible, then Godot would do the following checks in order. If the object has a script attached, it will attempt to set the property through the script. This leaves open the opportunity for scripts to override a property defined on a base object by overriding the setter method for the property. If the script does not have the property, it performs a hash map lookup in the class DB for the visible property against the canvas item class and all of its inherited types. If found, it will call the bound setter or getter. For more information about hash maps, see the data references docs. If not found, it does an explicit check to see if the user wants to access the script or meta properties. If not, it checks for a set get implementation, depending on the type of access. If the canvas item is inherited types, these methods can execute logic that gives the impression that the object has a property. This also gives the object the case that the get property list method. Note that this happens even for non-legal symbol names, such as names starting with a digit or containing a slash. As a result, this duck type system can locate a property either in the script, the object's class, or any class that object inherits, but only for things which extend object. Godot provides a variety of options for performing runtime checks on these accesses. A duck type property access. These will be property checks as described above. If the operation isn't supported by the object, execution will halt. A method check, in this case of canvas item visible, can access the methods set visible and is visible like any other method. Outsource the access to a callable. These may be useful in cases where one needs the max level of freedom from dependencies. In this case, one relies on an external context to set up the method. These strategies contribute to Godot's flexible design. Between them, users have a breadth of tools to meet their specific needs. Still got a bunch left. Godot, and by a bunch, I mean, once I'm done here and get down to troubleshooting, I think I'm gonna hop over to here and learn GD script. Godot notifications. Every object in Godot implements a notification method. Its purpose is to allow the object to respond to a variety of engine-level callbacks that may relate to it. For example, if the engine tells a canvas item to draw, it will call notification, notification draw. Some of these notifications, like draw, are useful to override in scripts. So much so that Godot exposes many of them with dedicated functions. Ready, notification ready, enter tree, notification enter tree, exit tree, notification exit tree, process delta, notification process, physics process delta, notification physics process, draw, notification draw. What users might not realize is that notifications exist for types other than node alone. For example, object notification post-initialization. Oh, post-initialization. Or no, yes. Post-initialize. I cannot read. Can you tell? A callback that triggers during object initialization, not accessible to scripts. Object notification pre-delete. A callback that triggers before an engine deletes an object, i.e. a destructor. And many of these callbacks that do exist in nodes don't have any dedicated methods, but are still quite useful. Node notification parented. A callback that triggers anytime one adds a child node to another node. Node notification unparented. A callback that triggers anytime one removes a child node from another node. One can access all these custom notifications from the universal notifications method. Why is this chair so squeaky? Squeak, squeak, squeak. You guys can't hear it though, I think. Yeah. One can access all the hair. Hair. One can access these custom notifications from the universal notification method. Note methods in the documentation labeled as virtual are also intended to be overridden by scripts. A classic example is the init method in object. While it has no notification equivalent, the engine still calls the method. Most languages, except C#, rely on it as a constructor. So, in which situation should one use each of these notifications or virtual functions? I don't know. You tell me. Let's see. Process. Process versus physics. Process versus input. Use process when one needs a frame rate dependent delta time between frames. If code that updates object data needs to update as often as possible, this is the right place. Recurring logic checks and data caching often execute here, but it comes down to the frequency at which one needs the evaluations to update. If they don't need to execute every frame, then implementing a timer timeout loop is another option. Uh, uh. Allows for recurring operations that don't trigger script logic every frame or even every fixed frame. Function ready, variable timer, timer new, timer auto start true, timer wait time 0.5 seconds, add child timer. Timer timeout, connect function. Print this block runs every 0.5 seconds. Okay, that's for testing purposes. Use physics process. When one needs a frame rate independent delta time between frames, if code needs consistent updates over time, regardless of how fast or slow time advances. This is the right place. Recurring kinematic and object transform operations should execute here. While it is possible to achieve the best performance, one should avoid making input checks during these callbacks. Process and physics process will trigger at every opportunity. They do not rest by default. In contrast, input callbacks will trigger only on frames in which the engine has actually detected the input. One can check for input actions within the input callbacks just the same. If one wants to use delta time, one can fetch it from the related delta time methods as needed. Callback every frame when the engine detects no input. Yep. If input is action just pressed, UI select, print delta. Okay. Callback during every input event. Function unhandled input event. Match event get class. Input event get key. So what does that do? If input is action just pressed, UI accept, print get process. Okay. I don't know what match does, but I think input event key, get that, and that's stored. If input is action just pressed, UI accept, print get process delta time. I don't know what any of that means. I don't know GD script. Ugh. Init versus initialization versus export. If the script initializes its own node subtree without a scene, that code should execute in init. Other property or scene tree independent initializations should also run here. Note, the C# equivalent to GD script's init method is the constructor. Init triggers before enter tree or ready, but before a script creates and initializes its properties. When instantiating a scene, property value will set up according to the following sequence. Initial value assignment. The property is assigned to assigned its initialization value or its default value if one is not specified. If a setter exists, it is not used. Init assignment, if the property's value is replaced by any assignments made in init, triggering the setter. Exported value assignment. An exported property's value is again replaced by any value set in the inspector, triggering the setter. As a result, instantiating a script versus a scene may affect both the initialization and the number of times the engine calls the setter. Test is initialized to 1 without triggering the setter. Export variable test, string equals 1, set value, test equals value plus exclamation mark. Function init triggers the setter, changes test value from 1 to 2. If someone sets test to 3 from the inspector, it would trigger the setter, changing test value from 2 to 3. Ready versus enter tree versus notification parented. When instantiating a scene connected to the first executed scene, Godot will instantiate nodes down the tree, making init calls and build the tree going downwards from the root. This causes enter tree calls to cascade down the tree. Once the tree is complete, leaf nodes call ready. A node will call this method once all child nodes have finished calling theirs. This then causes a reverse cascade going up back to the tree's root. When instantiating a script or a standalone scene, nodes are not added to the scene tree upon creation, so no enter tree callbacks trigger. Instead, only the init call occurs. When the scene is added to the scene tree, the enter tree and ready calls occur. If one needs to trigger behavior that occurs as nodes parent to another, regardless of whether it occurs as part of the main active scene or not, one can use the parented notification. For example, here is a snippet that connects a node's method to a custom signal on the parent node without failing, useful on data-centric nodes that one might create at runtime. Alright, got 4 left. Work in progress. The content of this page was not yet updated for Godot 4.6 and may be outdated. If you know how to improve this page, or you can confirm that it's up to date, feel free to open a pull request. Data preferences. Ever wondered whether one should approach problem X with data structure Y or Z? This article covers a variety of topics related to these dilemmas. This article makes reference to something time operations. This terminology comes from algorithm analysis, Big O Nation. What? What the fuck? Math? Big O notation. Describe the performance or complexity of an algorithm. Specifically describes the words that can be used to describe an execution. What? Oh, shit. Long story short, it describes the worst case scenario of runtime length. In layman's terms, as the size of a problem domain increases, the runtime length of the algorithm, constant time, 0, 1, does not increase. Logarithm time, 0 log n, increases at a slow rate. Linear time, 0 n, increases at the same rate, etc. Imagine if one had to process 3 million data points within a single frame. It would be impossible to craft a feature with a linear time algorithm, since the sheer size of the data would increase the runtime far beyond the time allotted. In comparison, using a constant time algorithm could handle the operation without issue. By and large, developers want to avoid engaging in linear time operations as much as possible. But if one keeps the scale of a linear time operation small, and if one does not need to perform the operation often, then it may be acceptable. Balancing these requirements and choosing the right algorithm or data structure for the job is part of what makes programmer skills valuable. Array versus dictionary versus object. Godot stores all variables in the scripting API, the variant class. Variants can store variant-compatible structures, such as array and dictionary, as well as objects. Godot implements array as a vector variant. The engine stores the array contents in a continuous section of memory, i.e. they are a row adjacent to each other. Note, for those unfamiliar with C++, a vector is the name of the array object in traditional C++ libraries. It is a templated type, meaning that its records can only contain a particular type, denoted by angled brackets. So, for example, a packed string array would be something like vector string. Contiguous memory stores imply the following operation performance. Iterate, fastest, great for loops. OP, all it does is increment a counter to get to the next record. Insert erase move, position dependent, generally slow. OP, adding, removing, moving. Content involves moving the adjacent records over to make room or fill space. Fast, add, remove from the end. Slow add, remove from an arbitrary position. Slowest, add, remove from the front. If doing many inserts, removals from the front, then invert the array. Do a loop which executes the array changes at the end. Reinvert the array. This makes only 2 copies of the array, still constant time but slow, versus copying roughly 1/2 of the array on average, n times linear time. Get, set, fastest position, e.g. can request 0th, 2nd, 10th record, etc., but cannot specify which record you want. Option, or OP, I don't know what OP means. OP, one addition operation from array start position up to desired index. Find, slowest identifies the index position of a value. OP must iterate through array and compare values until one finds a match. Performance is also dependent on whether one needs an exhaustive search. If kept ordered, custom search operations can bring it to logarithmic time, relatively fast. Layman users won't be comfortable with this though, done by resorting the array after every edit and writing an ordered aware search algorithm. Oh, Jesus, this section is long. Godot implements dictionary as hashmap variant hasher string-like variant comparator. The engine stores a small array initialized to 2 to the power of 3 or 8 records of key value pairs. When one attempts to access a value, they provided a key. It then hashes the key, i.e. converts it into a number. The hash is used to calculate the index into the array. As an array, the HM then has a quick lookup within the table of keys mapped to values. When the hash map becomes too full, it increases the next power of 2. So 16 records and 32, etc., and rebuilds the structure. Hashes are to reduce the chance of key collision. If one occurs, a table must recalculate another index for the value that takes the previous position into account. In all, this results in constant time access to all records at the expense of memory and some minor operational efficiency. Hashing every key an arbitrary number of times. Hash operations are constant time, so even if an algorithm must do more than one, as long as the number of hash calculations doesn't become too dependent on the density of the table, things will stay fast, which leads to 2. Maintaining an ever-growing size for the table. Hash maps maintain gaps of unused memory and interspersed in the table on purpose to reduce hash collisions and maintain the speed of accesses. This is why it constantly increases in size exponentially by powers of 2. As one might be able to tell, dictionaries specialize in tasks that arrays do not. An overview of their operational details is as follows. Iterate. Fast. OP. Iterate over the hash map over the map's internal vector of hashes. Return each key. Afterwards, users then use the key to jump and return the desired value. Insert, erase, move. Fastest. OP, hash the given key, do one addition operation to look up the appropriate value. Erase start plus offset. Move is 2 of these. 1 insert, 1 erase. The map must do some maintenance to preserve its capabilities. Update ordered lists of records. Determine if table density mandates a need to expand table capacity. The dictionary remembers in what order users inserted its keys. This enables it to execute reliable iterations. Get, set, fastest. Same as a lookup by key. OP, same as insert, erase, move. Find, slowest, identifies the key of a value. OP must iterate through records and compare the value until a match is found. Note that Godot does not provide this feature out of the box because they aren't meant for this task. Interesting. Godot implements objects as stupid but dynamic containers. What do they mean by stupid? Of data content. Objects query data sources when posed questions. For example, to answer the question, do you have a property called position? It might ask its script or the class DB. One can find more information about what objects are and how they work in the Applying Object-Oriented Principles in Godot article. The important detail here is the complexity of the object's task. Every time it performs one of these multi-source queries, it runs through several iteration loops and hash map lookups. What's more, the queries are linear time operations dependent on the object's inheritance hierarchy size. If the object queries its current class doesn't find anything, the request defers to the next base class, all the way up until the original object class. While these are each fast operations in isolation, the fact that it must make so many checks is what makes them slower than both the alternatives for looking up data. Note, when developers mention how slow the scripting API is, it is this chain of queries they refer to, compared to compiled C++ code where the application knows exactly where to go to find anything. It is inevitable that scripting API operations will take much longer. They must locate the source of any relevant data before they can attempt to access it. The reason GDScript is slow is because every operation it performs passes through this system. C# can process some content at higher speeds via more optimized bytecode, but if the C# script calls into the engine's class content, or if the script tries to access anything external to it, it will go through this pipeline. NativeScript C++ goes even further and keeps everything in internal by default. Calls into external structures will go through the scripting API in NativeScript C++, registering methods to expose them. To the scripting API is a manual task. It is at this point that external non-C++ classes will use the API to locate them. So assuming one extends from reference to create a data structure like an array or dictionary, why choose an object over the other two options? Control. With objects comes the ability to create more sophisticated structures. One can layer abstractions over the data to ensure the external API doesn't change in response to internal data structure changes. What's more, objects can have signals allowing for reactive behavior. Clarity. Objects are Clarity. Objects are a reliable data source when it comes to the data that the scripts and engine classes define for them. Properties may not hold the values one expects, but one doesn't need to worry about whether the property exists in the first place. Convenience. If one already has a similar data structure in mind, then extending from an existing class makes the task of building the data structure much easier. In comparison, arrays and dictionaries don't fulfill all use cases one might have. Objects also give users the opportunity to create even more specialized data structures. With it, one can design their own list, binary search tree, heap, splay tree, graph, disjoint set, and any host of their options. Why not use node for tree structure, one might ask. Well, the node class contains things that won't be relevant to one's custom data structure. As such, it can be helpful to construct one's own node type when building tree structures. From here, one can create their own structure with specific features, limited only by their imagination. And computer capabilities, of course. Most languages offer an enumeration type option. GDScript is no different, but unlike most other languages, it allows one to use either integers or strings for the enum values. The latter only when using the export enum annotation in GDScript. The question then arises, which should one use? The short answer is whichever you are more comfortable with. This is a feature specific to GDScript and not Godot scripting in general. The language prioritizes usability over performance. On a technical level, integer comparisons, constant time, will happen faster than string comparisons, linear time. If one wants to keep up other languages conventions though, then one should use integers. The primary use with using integers comes up when one wants to print an enum value. As integers, attempting to print my enum will print 5 or what have you, rather than something like my enum to print an integer enum. One would have to write a dictionary that maps the corresponding string value for each enum. If the primary purpose of using an enum is I'm getting a call. I'm currently
The shadows loom. Those creatures look hungry. How will you outsmart them this time? Share your next move.
Got a call from my grandmother. Okay. Alright. Enumerations, int versus string. Most languages offer an enumeration type option. GDScript is no different, but unlike most other languages, it allows one to use either integers or strings for their enum values. Shelby. Doggo. Strings or enum values. The latter only when using the export enum annotation in GDScript. The question then arises, which should one use? The answer is whichever you are more comfortable with. This is a feature specific to GDScript and not Godot scripting in general. The language prioritizes usability over performance. On a technical level, integer comparisons, constant time, will happen faster than string comparisons, linear time. If one wants to keep up other languages conventions though, then one should use integers. The primary issue with using integers comes up when one wants to print an enum value, as integers attempting to print my enum will print 5 or what have you, rather than something like my enum to print an integer enum. One would have to write a dictionary that maps the corresponding string value for each enum. If the primary purpose of using an enum is for printing values and one wishes to group them together as related concepts, then it makes sense to use them as strings. That way, a separate data structure to execute on the printing is unnecessary. I need to pull something up. Nope. Okay, if I go here, and this is my current stream. Yes, yes, yes. Am I not live? Am I not? Am I not live? Gotta refresh this. Am I? Okay, I am. And if I come here, okay, it does. Am I not live? Okay, okay. I am live. Okay, fucking YouTube making me think I'm not. Channel dashboard. Dash. Let's see, how many did we get? One whole views! Yay! one whole views. Concurrent viewers. That, yay. Already learning shit. Watch 3.7 hours. Damn. Somebody was interested. I wonder who. Languages, 2 languages. Yeah, I'm not even close. Customization. Yeah, check these out. Check them out. Check them out. Do it. Dare you. Audio library. Yeah. I should do that. Recount is at greater risk. Dismiss. Content. Live. This one. Description. What's wrong with the description? Oh, shut up. Visibility public, of course. No, of course not. I should probably put on tags. But I don't wanna do that. I don't wanna. Oh, save changes. Customization. Live chat reply? I don't need a live chat summary. I simply just do not need that. No. What is this? I shall send anytime someone watches the video recording. Oh, yeah. Anyone. Analytics. Reach. Channel pages. What? Engagement. Average view duration. What? Then how did... Then... Oh, this is for this stream. Oh, okay. Somebody popped in for a second. Or are they still here? No, they're not. I cannot... I cannot tell. Somebody here? Clips. I'll work on that. Yeah. Views, that's so interesting. Analytics. That's just wild. 3.7 3.7 hours. That's crazy. Impressions 7. Damn. YouTube search. All right, I guess we get back to it if people are actually kind of interested in this. Animated texture versus animated 2D sprite versus animated player versus animation tree. Under what circumstances should one use each of Godot's animation classes? The answer may not be immediately clear to new Godot users. Animated texture is a texture that the engine draws as an animated loop rather than a static image users can manipulate. The rate at which it moves across each section of the texture FPS, the number of regions contained within the texture, frames, Godot's rendering server then draws the regions in sequence at the prescribed rate. The good answer is that it involves no extra logic on the part of the engine. The bad news is that users have very little control. Also know that the animated texture is a resource. Unlike the other node objects discussed here, one might create a Sprite 2D node that uses animated texture as its texture, or it's something the others can't do. One could add animation textures as tiles in a tile set, and integrate it with a tile map layer for many auto-animating backgrounds that all render in a single batched draw call. The animated sprite node, in combination with the sprite frames resource, allows one to create a variety of animation sequences through its sprite sheets, flip between animations, and control their speed, regional offset, and orientation. This makes them well suited to controlling 2D frame-based animations. If one needs to trigger other effects in relation to animation changes, for example, create particle effects, call functions, or manipulate other peripheral elements besides the frame-based animation, then one will need to use an animation player node in conjunction with the animated sprite 2D. Animation players are also the tool one will need to use if they wish to design more complex 2D animation systems, such as cutout animations, editing sprites, transforms at runtime, 2D mesh animations, defining region for the sprite's texture, and rigging a skeleton to it. Then one animates the bones, which stretch and bend the texture in proportion to the bones' relationships to each other. A mix of the above. A mix of the above. While one needs an animation player to design each of the individual animation sequences for a game, it can also be useful to combine animations for blending, i.e. enabling smooth transitions between these animations. There may also be a hierarchical structure between animations that one plans out for their object. These are the cases where the animation tree shines. One can find an in-depth guide on using the animation tree here. Logic preferences. Ever wondered why one should approach problem X with strategy Y or Z? This article covers a variety of topics related to these dilemmas. Adding nodes and changing properties, which first? When initializing nodes from a script at runtime, you may need to change properties such as the node's name or position. A common dilemma is when should you change those values. It is best practice to change values on a node before adding it to the scene tree. Some property setters have code to update or other corresponding values that the code can be slow. For some cases, this code has no impact on your game's performance, but in heavy use cases such as procedural generation, it can bring your game to a crawl. For those reasons, it is usually best practice to set the initial values of a node before adding it to the scene tree. There are some exceptions where values can't be set before adding to the scene tree, like setting global position. Loading versus preloading. In GDScript, there exists the global preload method. It loads resources as early as possible. Holy dog hair. As early as possible to the front load the loading operations and avoid loading resources while in the middle of performance-sensitive code. Its counterpart, the load method, loads a resource only when it reaches the load statement. That is, it will load a resource in place, which can cause slowdowns when it occurs in the middle of sensitive process. The load functions is also an alias for resource loader load path, which is accessible to all scripting languages. So when exactly does preloading occur versus loading? When should one use either? Let's see an example. mybuildings.gd extends node. Note how constant scripts or scenes have a different naming scheme than their property variants. This value is a constant, so it spawns when the script object loads. The script is preloading the value. The advantage here is that the editor can offer auto-completion since it must be static path. Constant building scene, preload, building TSCN. The script preloads the value, so it will load as a dependency of the mybuilding.gd script file. But because it is a property rather than a constant, the object won't copy the preloaded packed scene resource into the property until the script instantiates with .new. The preloaded value is inaccessible from the script object alone. As such, preloading the value here actually does not provide any benefit. 3. Because the user exports the value, if the script stores on a node in the scene file, the scene instantiation code will overwrite the preloaded initial value anyway, wasting it. It's usually better to provide null, empty, or otherwise invalid default values for exports. Instantiating the script on its own with .new triggers load office tscn, ignoring any value set through the export. Export variable a building, packed scene, preload office tscn. Uh-oh, this results in an error. One must assign constant values to constants because load performs a runtime lookup by its very nature. One cannot use it to initialize a constant. Constant office scene load office. Successfully loads and only with when one instantiates a script. Yay! Yep. Preloading allows the script to handle all the loading uh, moment one loads the script. Preloading is useful, but there are also times when one doesn't wish to use it. Here are a few considerations when determining which to use. If one cannot determine when the script might load, then preloading a resource, especially a scene or script, could result in additional loads one does not expect. This could lead to unintentional variable length load times on top of the original script's load operations. If something could replace a value, like a scene's exported initialization, then preloading the value has no meaning. The point isn't a This point isn't a significant factor if one intends to always create the script on its own. If one wishes only to import another class resource, script, or scene, then using a preloaded constant is often the best course of action. However, in exceptional cases, one may wish not to do this. If the imported class is liable to change, then it should be a property instead, initialized either using an export or a load, and perhaps not even initialized until later. If the script requires a great many dependencies and one does not wish to consume so much memory, then one may wish to load and unload various dependencies at runtime and circumstances as run as at runtime as circumstances change. If one preloads resources into constants, the only way to unload these resources would be to unload the entire script. If they are instead loaded as properties, then one can set these properties to null and remove all references to the resource, which as a ref counted extending type will cause the resources to delete themselves from memory. Large large level static large level static versus dynamic. If one is creating a large level, which circumstances are most appropriate? It is better to create the level is it better to create the level as one static space, or is it better to load the level in pieces and shift the world's content as needed? The simple answer is when the performance requires it. The dilemma associated with the two options is one of the age-old programming choices. Does one optimize memory over speed, or vice versa? The naive answer is to use a static level that loads everything at once, but depending on the project, this could consume a large amount of memory. Wasting users' RAM leads to programs running slow or outright crashing from everything else the computer tries to do at the same time. No matter what, one should break larger scenes into smaller ones to aid in reusability of assets. Developers can then design a node that manages the creation / loading and deletion / unloading of resources and nodes in real time. Games with large and varied environments or procedurally generated elements often implement these strategies to avoid wasting memory. On the flip side, coding a dynamic system is more complex. It uses more programming logic, which results in opportunities for errors and bugs. If one isn't careful, they can develop a system that bloats the technical debt of the application. As such, the best options would be 1. Use static levels for smaller games. 2. If one has time or resources on a medium/large game, create a library or plugin that can manage nodes and resources with the code. If refined over time so as to improve usability and stability, then it could evolve into a reliable tool across projects. Use dynamic logic for a medium/large game because one has the coding skills, but not the time or resources to refine the code. Games gotta get done. Could potentially refactor later to outsource the code into a plugin. For example, of the various ways one can swap scenes around at runtime, please see the change scenes manually documentation. Project organization. Introduction. Since Godot has no restrictions on project structure or file system usage, or excuse me. Since Godot has no restrictions on project structures or file system usage, organizing files when learning the engine can seem challenging. This tutorial suggests a workflow which should be good at start which should be a good starting point. We will also cover using version control with Godot. Why? Okay, it's just a subcategory. Organization. Godot is scene-based in nature and uses the file system as is, without metadata or an asset database. Unlike the other engines, other engines, many resources are contained within the scene itself, so the amount of files in the file system is considerably lower. Considering that, the most common approach is to group assets as close to the scene as possible. When a project grows, it makes it more maintainable. As an example, one can usually place into a single folder their basic assets such as sprite images, 3D model meshes, materials, and music, etc. They can use a separate folder to store build levels that use them. Style guide. For consistency across projects, we recommend following these guidelines. Use snake-case for folder and file names, with the exception of C# scripts. This sidesteps case sensitivity issues that can crop up after exporting a project on Windows. C# scripts are an exception to this rule, as the convention is to name them after the class name, which should be in Pascal case. Use Pascal case for node names, as this matches built-in node casing. In general, keep third-party resources in a top-level add-ons folder, even if they aren't editor plugins. This makes it easier to track which files are third-party. There are some exceptions to this rule. For instance, if you use third-party game assets for a character, it makes more sense to include them within the same folder as the character scenes and scripts. Importing. Godot versions prior to 3.0 did the import process from files outside the project. While this can be useful in large projects, it resulted in an organization hassle for most developers. Because of this, assets are now transparently imported from within the project folder. Ignoring specific folders. To prevent Godot from importing files contained in a specific folder, create an empty file called gdignore. In the folder, the leading dot is required. This can be useful to speed up the initial project importing. Note: to create a file whose name starts with a dot on Windows, place a dot at the beginning and end of the file name. .gdignore dot. Windows will automatically remove the trailing dot when you confirm the name. Alternatively, you can use a text editor such as Notepad++ or use the following command in a command prompt. Type null less than value .gdignore. Once a folder is ignored, resources in that folder can't be loaded anymore using the load and preload methods. Ignoring a folder will also automatically hide it from the file system dock, which can be useful to reduce clutter. Note that just speak. Note that the .gdignore file's contents are ignored, which is why the file should be empty. It does not support patterns like .getignore files do. Case sensitivity. Windows and recent macOS versions use case-insensitive file systems by default, whereas Linux distributions use a case-sensitive file system by default. This can cause issues by exporting a project, since Godot's PCK virtual file system is case-sensitive. To avoid this, it's recommended to stick to a snake case naming for all files in the project, and lowercase characters in general. Note: you can break this rule when style guides say otherwise, such as the C# style guide. Still be consistent to avoid mistakes. On Windows 10, to further avoid mistakes related to case sensitivity, you can also make the project folder case sensitive. After enabling the Windows System for Linux feature, run the following command in the PowerShell window. To enable case sensitivity, fsutil file set case sensitive info, path to project folder, enable. To disable case sensitivity, same thing, just disable at the end instead of enable. If you haven't enabled the Windows subsystem for Linux, you can enter the following line in PowerShell window running as administrator, then reboot when asked. Enable Windows optional feature, online feature name Microsoft Windows Subsystem Linux. I think I have it enabled. I think I do. Last section. Version control systems. Introduction. Godot aims to be VCS friendly and generate mostly readable and mergeable files. Version control plugins. Godot also supports the use of version control systems in the editor itself. However, version control in the editor requires a plugin for the specific VCS we're using. As of October 2025, there is only a Git plugin available, but the community may create additional VCS plugins. Official Git plugin. Using Git from inside the editor supported with an official plugin. You can find the latest releases on GitHub. Documentation on how to use Git plugin can be found on its wiki. Gonna save that. Files to exclude from VCS. Note this lists files and folders that should be ignored from version control in Godot 4.1 and later. The list of files and folders that should be ignored from version control in Godot 3.x and Godot 4.0 is entirely different. This is important as Godot 3.x and 4.0 may store sensitive credentials in export presets.config, unlike Godot 4.1 and later. If you are using Godot 3, check the 3.6 version of this documentation page instead. There are some files and folders Godot automatically creates when opening a project in the editor for the first time. To avoid bloating your version control repository and generated data, you should add them to your VCS ignore. Godot. This folder stores various project cache data. *.translate. These files are binary imported translations generated from the CSV files. You can make the Godot project manager generate version control metadata for you automatically when creating a project. When choosing the Git option, this creates Git ignore and Git attributes files in the project root. Creating version control metadata in the project manager's new project dialog. In existing projects, select the project menu at the top of the editor. Then choose version control. Generate version control metadata. This creates the same files as if the operation was performed in the project manager. Working with Git on Windows. Most Git for Windows clients are configured with the core auto-crlf set to true. This can lead to files unnecessarily being marked as modified by Git due to their line endings being converted from LF to CRLF automatically. Bleh. I'm gonna put this over here. Honk. Where was I? Automatically, yes. It is better to set this option as git config global core auto-crlf input. Creating version control metadata using the project manager or editor will automatically enforce LF line endings using the .git attributes file. In this case, you don't need to change your Git configuration. Git LFS. Git LFS files large file storage is a Git extension that allows you to manage large files in your repository. It replaces large files with text pointers inside Git while storing the file contents on a remote server. This is useful for managing large assets, such as textures, audio files, and 3D models without bloating your Git repository. Note, when using Git LFS, you will want to ensure it is set up before you commit any files to your repository. If you have already committed files to your repository, you'll need to remove them from the repository and re-add them after setting up Git LFS. It is possible to use Git LFS migrate to convert existing files to your repository, but this is more in-depth and requires a good understanding of Git. A common approach is setting up a new repository with Git LFS and a proper Git attributes, then copying the files from the old repository to the new one. This way you can ensure that all files are tracked by LFS from the start. To use Git LFS with Godot, you need to install the Git LFS extension and configure it to track the file types you want to manage. You can do this by running the following command in your terminal: git lfs install. This will create a Git attributes file in your repository that installs Git to the LFS for the specified file types. You can add more file types by modifying the Git attributes file. For example, to track all GLB files, you can do this by running the following command in your terminal: git lfs track *.glb. When you add or modify files that are tracked by LFS, Git will automatically store them in LFS instead of the regular Git history. You can push and pull LFS files just like regular Git files, but keep in mind that LFS files are stored separately from the rest of your Git history. This means you may need to install Git LFS on any machine that you clone the repository to in order to access the LFS files. Below is an example git.get attributes, the file that you can use as a starting point for Git LFS. These file types were chosen because they are commonly used, but you can modify the list to include any binary types you may have in your project. Normalize whoa. Normalize EOL for all files that Git considers text files. Text auto EOL LF. Git LFS tracking assets, 3D models, images, audio, font, and icon. Godot LFS specification. For more information on Git LFS, check the official documentation. Git LFS, GitHub, and that. Troubleshooting. Oh, seriously? It's just one? I I guess best practices was rather long, I suppose. Let's say XR. How long are you? 3? 4? Oh, shaders is long. Scripting, of course. Though, probably not going to go through these 3, just those 2. Just these 3. Alright, not that one. This one. This is completed practice. Yeah, shader scripting, rendering. Alright, plugins. 2. Platform specific. I think we're fine on that. Physics. I will not need to read all of that. Performance. Don't need to go through 3D. Networking. Maybe. Navigation. Math. Of course. Of course. Love math. Math's great. Super interesting. Input handling. Internalization. File and data I/O. Whoa. Export. Whoa. Audio. Assets pipeline. Animation. Don't need 3D. 2D. Migrating to a new version. Editor introduction. Troubleshooting. And we're currently in troubleshooting. Who the hell? Another one? Okay, interesting. Alright, let's start. Learning to program can be daunting, yet you want to make video games. So there is no way around learning to program. Every video game is a computer program, telling the computer what to do. Programming is the process of writing precise instructions that tell the computer how to perform a task. I should pull Streamlabs. Hi!
What are you doing?
Learning more Godot.
Ah,
What do you think I'm doing in here?
I was about to say something really stupid and then remembered you were live.
Uh-huh, uh-huh. Yeah, don't say that stupid thing.
You don't even know what it was.
I don't. But if you said it was something uh that you shouldn't have said while I'm live,
It's
then
something rich people like to
I
do.
have a good
Like,
guess. I have a couple good guesses here.
it's actually not a slur.
It's
It's
not a
something that
slur.
rich people like.
It's what?
Something that rich people like to do, apparently.
Ah. And what is that? There are a few things that they like to do.
Island, a certain
Crimes?
one.
They love to do crimes.
That they do.
Yeah, they do. They do. Oh, by the way, Saturday, fun thing. You see, I
Mm-hmm.
have a dinner party to go to at 3.
Right, right.
Yeah, yeah. That's all. Just a heads up on that. So,
So
I'll
probably not doing the trial recording on Saturday.
we can do it if we do it early.
Uh, how early do you think we're all going to be awake? Because we also have the food order to pick up at 1:30,
You're
and they give
right.
us 10 minutes to be there.
You're right. You're absolutely right. We can split it into two, probably.
Just do two little sections the day, okay.
Yeah, yeah, I mean, just, yeah, shouldn't be that bad.
And just pray that we don't have to wait until after your dinner party to truly finish it. Or I guess we could just do that to be safe anyway.
Um, I don't know. 'Cause how long should it take?
The second trial for 5-3 is really long.
Okay, how long is it?
Oh, let me seeing I can do that.
So that we can properly plan shit out.
But
We're gonna have to have Jesse wake us up. I know that.
me when I have an alarm.
Or that.
That's actually not quite as bad as I thought it was. This video is 6 hours long. The second trial starts at 3 hours and 52 minutes.
So
So
2 hours.
it's like a
4 hours.
3 hour trial, yeah.
Alright, so I'm going to be leaving at 2:30. Let's say 30 minutes for the bishop order, right? Just
It won't take you close to that long, but yeah.
just to be safe. Just to be safe.
I know. But we've
So
done this before. It takes you 5 minutes.
5 minutes, huh? How long does it take to get over there, though?
To get there, probably like 6 minutes, I think, if traffic is fine.
Okay, so we'll have 15 minutes. Then, so what is it from again?
1:30 to 1:40.
130, 140. So we'll have
That is the time window we have to get there.
30, 40, 50 minutes afterwards. So, gonna have to
So, like, unless you intend to get up at like
9.
8, which Jesse probably won't.
Yeah, okay. We'll just have to split it into two then. Um, one beforehand and then before the bishop order and then we'll and then once I get back.
Yeah.
That sounds like the best way to split it. Who the? Ah, my mother. I have to talk to her about it. Yeah, I'll be right back. I'm gonna go talk with her about that.
I Oh, right. That's the Windows default now. Huh? What? I don't.
You can stop whenever I'm done and we hang out. Just turn something on the TV or something. All right. My mother is okay with picking me up and dropping me off. Ethan?
Okay.
Okay.
Yeah, I'm here. I'm just doing something.
Let me guess. Marvel Rivals.
Nope.
No. Oh. Seriously?
Seriously. Do you want to see what I'm trying to do?
Sure.
It's this neat little thing called not finding an extension I like of certain songs, so I'm making it myself.
Oh.
And that worked. So
Cool.
now comes the really easy part.
Wait. What is this for?
Shits and giggles
You're just extending it for no reason?
for fun.
Okay.
Because I like listening to music on repeat, and extensions make it loop less often.
Yeah. Tasty.
I'm very smart. I need to fucking actually like put the ending in here so it doesn't just end like this.
No, it's funny.
Look, it works with the Game 3 Pursuit theme, which I already extended and uploaded,
Mm-hmm.
but not this one.
He's he's extending the pursuit theme for Ace Attorney.
Specifically Ace Attorney 2.
Yeah. Ugh.
I just finished doing Dual Destinies and uploaded that.
I should mute your stream because copyright.
There is no copyright issues with the Ace Attorney music. Don't worry about
Really?
it.
Really?
Hmm.
Hmm.
Yep, it's
Interesting.
royalty free.
Interesting. Hey,
Now, if I was
Ethan.
extending something from other games, then it would be an issue.
Ethan.
What?
K- Do you think it possible for you to maybe not right now, but make a background music playlist for my streams?
With a lack of royalty music?
Yes.
You would never believe what I already have, actually.
You already have one of those. Oh my God, that's awesome.
Yeah, I made one a little while ago.
Um,
Uh,
also, uh, you may have that, but do you think you could trim the songs that might not fit the vibe of the Learning Godot or just my programming series? So like
yeah, I can do that.
Roaring Blade or shit like that,
Bring Blade.
or whatever the song is called for the night.
Black Knife.
Yes, that one. Shut
Uh,
up.
okay, so like, huh? How do you think like Ace Attorney music would fit in with that?
Um, just take the stuff that is more distracting out. I trust in your abilities. What?
Right. So distracting
Oh,
stuff, get the fuck out.
Zach went to. He's at an appointment.
Um,
You can show him later.
like,
Sorry. Yeah, just more distracting music. Just take it out.
so Calamity Mod music is gone.
Yeah. Anyway, telling the computer what to do. Programming is the process of writing precise instructions that tell the computer how to perform a task. Really?
You know,
No shit.
I should
No
probably
shit.
just make a whole new playlist
Yeah.
looking at this.
Too long to go through.
It's 194 songs after already removing a few.
Mm-hmm. Mm-hmm.
So like, and a lot of them are probably not what you want to be listening to while coding.
Or reading.
I mean, yeah, probably not. But I mean,
You can
I
take a.
can do anything.
Oh, I suggest taking a look at the Amori OST because some of those are really neat.
Okay, I'm gonna let you take a look at this, what it is right now, and
Uh-huh.
you tell me.
Uh-huh.
I know like 90% of it is already gonna get cooked.
Well, first of all, a lot of the Ultra Kill stuff is going to be out.
I'm well aware.
Um, Risk of Rain isn't a bad choice. Um, I really like Undertale and Deltarune, but like it's distracting for me because I love it so much.
Okay, so take Dark Zone out of the new one I just made.
Um, there are some songs that you can add that are more chill, but like,
Yeah,
yeah, yeah.
maybe not Providence's boss theme.
Probably not.
Um,
I don't know what Ace Attorney songs, but probably some of them. Maybe not the Pursuit theme though, because that one's more upbeat. I don't know. You're more familiar with the Ace Attorney music than I am.
that I am. Shut the fuck up.
Hmm.
I know Ruby music has copyright issues, so none of that.
You can definitely do the Undertale Yellow, because I'm not as familiar with that.
Okay. I haven't listened to the majority of the Undertale Yellow soundtrack, though. What I have listened to is the boss themes, which are the bad for this.
I would love to have Black and Moonsetter in there, but one, I don't know what the individual copyright shit is for those songs. Um,
I have used black in my videos before, and I don't think it's caused an issue. Let me check.
then again, you aren't monetized, so it isn't as big of a deal.
That is true, but it would still tell me if there are copyrighted audios in my videos.
Yeah, but I don't want to use Homestuck music
Right, that's
because
fair.
all the songs are copyrighted by different people and everybody has different copyright rules about their music, so it's just best not to use it in general.
Yeah. It looks
Unless
like
you're, of
black
course,
at the very
going,
least is safe.
at least, of course, when you're going through Homestuck anyway. I would still take it out anyway. I don't
Yeah, that's
wanna,
fair.
I don't wanna mess with that. Yeah, take a look at the Ormori soundtrack. That one's tasty.
Okay. I'd have to listen to it first.
Yeah, yeah, it's. Here, I'll send you a link to it. Oh, where is it? Why do I not have this bookmarked? It's 3 hours.
Okay. I wish the Persona soundtrack didn't have royalties on it, but
I don't know if the Amori OST has royalties.
um I could make like a quick single Marvel Rivals video, like a single match with it and see.
Guidelines, images, and media on the Amori wiki must be. All images must have a license template appear on the file page. The license template must be correct. Any Amori images, screenshots, audio clips, or other content extracted from game files or artwork concept images should use the following templates. Do not mark any of these content using other licenses or claiming it. Artwork, audio Amori for use on audio files extracted from the game. Content that is free. Files on Amori wiki must be accompanied by licensing. Um, but I believe that only my time is copyrighted. All the tracks don't have any copyright. At least from what I can tell on YouTube, if you need an explanation, YouTube puts extra information on the owner and copyright song usually. The video contains such song. Cat's channel. That doesn't seem to be such informations. Um, it doesn't look like the Amori OST has any copyright issues.
I
So we'll just, if there are, I'll just have to worry about that. Why is my
okay.
sister? Okay. Um, a game's instructions are, for example, moving a character, drawing a life bar, or playing a sound. To do any of that, you need to learn a programming language, a specialized language to tell the computer what to do. Programming languages are
Really?
different from natural ones like English or Spanish. The computer does not think, unlike us, it can't interpret what you tell it. You can't tell it something vague like draw a circle. Which circle? Where? What color should it be? How big should it be? The computer needs exact instructions. To draw a filled circle, the computer needs to know exact drawing coordinates, the radius, the thickness, and color you want. The code to do so may look like this. Click the button to run the sample and see the result. Huzzah! Draw a circle. Vector 2, 0, 0, 60. I'm assuming the 60 is the radius and not the diameter. Color aqua. If in the following lessons you'll learn how this code works. For now, we want to give you a sense of what computer code looks like. In this example, everything matters. Each parentheses, capital letter, period, and comma. The computer always does exactly what you tell it to, no more, no less. It blindly follows every instruction. When you program, you're the one in charge. You're free to do anything you want. How do you give instructions to a computer? Using prose in plain English. No, using a programming language and precise instructions.
What the fuck, Chris Christodoulou?
Chris.
He's the guy who made the Risk of Rain soundtrack. One of the Risk of Rain song names is just a fucking set of coordinates.
Oh, that's weird.
What?
Hey, Ethan, you want to take a look at some of the games that have been made in Godot?
But I'm building your playlist.
It'll just be real quick. Okay, I'll just list them. Brotato, Dome Keeper, that Cruelty Squad. Oh, that game. Buckshot Roulette.
It was?
Yeah, Halls of Torment. Oh, fuck off. The Case of the Golden Idol. Luck Be a Landlord. Endoparasitic. Window Kill. X Zodiac. Delta V Rings of Return. Gordlets. Or Delta 5.
Do you think it could maybe be Delta 5?
Yeah, no, yeah. City Game Studio, your game dev adventure begins. Sonic Colors, Cat Cafe Manager, Lumencraft, Rogue State Revolution, Blastronaut, Resolution, Cassette Beasts, Primal Light, Gravity Ace, Heike, Of Life and Land, The Garden Path, Kameru, A Frog Refuge, Until Then, SCP Bloodwater. What?
Okay.
What the? Usagi-shima, Kingdoms of the Dump, Hive Time, Toziu Ha Night OOTA Prelude, Backpack Battles, Project Cat Paper Lily Prologue, The Interactive Adventures of Dog Mendoka and Pizza Boy. Those are just some. A lot of those I don't know.
Yeah. So, I already have 50 songs in this new playlist.
Cool.
It's 2.5 hours long already, but
All right.
you're probably going to be going for longer than that.
Oh, yeah. I'm gonna shuffle it, obviously.
Well, duh.
But you'll learn to code with GDScript. In this course, you'll learn the GDScript programming language. The name stands for Godot Script. This is a language by game developers for game developers. You can use it within the Godot game engine to create games and applications. It's a language used by games like Dome Keeper and Brotato. Engineers at Tesla also use it for their cars' dashboards. What? What?
Sure. Also,
Okay.
so fun fact about some of the upcoming Ace Attorney games.
Oh.
Like Great Ace Attorney and the Professor Layton game.
Mm-hmm.
You cross-examine multiple witnesses at once in those.
Ah, what?
I
Uh,
don't know how it works, but you have multiple people testifying at the same time.
that, uh, huh? How?
Yeah, I don't know.
GDScript is an excellent language to get started programming because it's specialized. Unlike some other languages, it doesn't have an overwhelming amount of features for you to learn. Most programming languages are similar. Don't be afraid of being locked in. The concepts you learn in your first programming language will apply to all the others. What?
Nothing.
I, don't be surprised for some of the language that it employs, because it's from what the fuck?
Uh,
Because Godot is a community-driven thing, it's going to have less professional language than something like Unity
God.
game engine.
Lyndon.
What?
Uh, one of the songs that I've just seen in the suggested thing to put in the playlist. It's a Dual Destinies track.
Mm-hmm.
Do you want to guess what it's named?
I don't know. Password is 1234.
The Dark Age of Law.
Oh!
The fucking Dark Age of the Law.
The Dark Age of the Law. Can't take it any seriously. Most programming
No, I
languages
can't.
are similar. Don't be afraid of being locked in. The concepts you'll learn in first spoken language will apply to all the others. Yeah, you already get it. Most languages have more similarities than differences. Once you learn one, it takes much less time to become productive with the next one. Here's an example of the same code in three languages: GDScript, JavaScript, and Python. Try to spot the similarities and differences. Um, well, first of all, they all start off with, hey, this is a function, and then the function name, and then the parameter that you put in it. And then inside, you have the health um, variable minus the amount variable. And if health is less than 0, then die. So
You should
it's
code
not.
your entire game in one big if-then statement.
Is this going. I. Well, for one, I can't exactly do that. But I can do that to the best of my abilities. I know Undertale
Uh,
was coded like that.
Balatro was also coded similarly.
Yeah, but I don't know. I'm just gonna code it how I code it. It may be a big if statement, but it could also not be a big if statement. It could
Hi,
just
FedEx truck.
buy FedEx truck.
It's just sitting outside.
Doesn't look that different, does it? Our programming language is all completely different. If you learn one language and then want to learn another, have, will you have to start from scratch? No, they have many similarities. This is a course for beginners, blah 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 blah. Healing gems or blah 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 blah. Okay, all I want to do is learn GDScript. I don't care about it. Oh, he's deafened. I don't care about anything else. Ah. Goals. We prepared a code sample for you. For this practice, you don't need to change anything. To test the code, click the Run button below the code editor. Run. Good. Function ready. Print welcome. You completed the practice. Stay and play around or continue the course. Yay. When you program, errors. Yeah. Are error messages a good or bad thing in code? They're good. They're there to help. They're bad. Error messages are always bad. They're always bad. No, it's like attributing the symptoms to as the problem. Um, the error message is just there to indicate that there is a problem. So the error messages aren't bad. The bad thing is what they're indicating. Function, this code is wrong. Return. This code is incorrect and will cause an error when you try to run it. The code defines an empty function named this code is wrong. To work, the function should use the return keyword, but this keyword is currently inside a comment, which the computer ignores. Adjust the current code by pressing the run button, then remove the comment sign to make the code valid. Blah blah blah, return. It doesn't work, so and it returns. Running tests. Yay. Continue. Lesson complete. We stand on the shoulders of giants as programmers. We learn creative authors perform us. You always have a lot of existing code, calling functions, blah blah blah. In the code listed above, we write the function call hide in a new function named run to execute the code. Creating a new function is necessary to execute instructions in GDScript. Functions argument. We use parentheses to call functions because you can give them the function arguments inside the parentheses when calling it. Oh, okay, he just stopped watching my stream. Parentheses call functions because you can give the function arguments inside the parentheses when calling. Here's a sprite standing straight. If we call the rotate 0.3 function, the character sprite turns by 0.3 radians. The 0.3 part between the parentheses in the function's argument is the function's argument. Arguments are values, numbers, bits of text, and more that change how the functions behave. Arguments let you fine-tune the effect of your function call, blah blah blah, I already know. What does the code below do? Show. It calls the function named show and makes the entity, like a game character or a sprite, visible. Yep, it does both of those. Another example with the move local x function, you can move the character to its left and right. The function takes one argument, a number of pixels, to the offset of the entity. The complementary function, move local y, makes the character move up and down. This is one way to move a character in a game, although we'll see more powerful ways to do this later. And this one also runs. Balls.
Ugh.
I'm gonna rotate you.
Please don't. I don't want to be rotated.
Why not?
I don't want to rotate.
But I wanna rotate you. Doesn't
I
that
don't
sound
want to
fun?
rotate.
But
I don't want to rotate.
Nah, you're gonna get rotated.
No.
Yes.
No.
Rotation is the name of the game.
No, it's not.
You're right. The first part of the game is called the Black Hex Code. What? Why are you silent? Don't object to me. Stop that. Hold it. Take that.
No.
I don't know what you're taking, but it's something. No. Quit it with your soundboard. Why do you call a function? What is the syntax you use to call a function in general? No.
What do you mean no?
No. It means no.
You can.
Don't.
You can.
Chair, don't squeak. Chair, no
Too bad.
squeaking. Ah.
Chair squeak.
God damn it. How do you call a function? What is the syntax you use to call a function in general? You write its name followed by an opening and closing parentheses. You write a value like a number followed by an opening and closing parentheses. Followed by? No. You write its name followed by a colon. No. It's the first one. Oh, two practices. Make the character visible. A robot character is invisible. Call the show function to make it appear. Please call show inside the run function on line 2 and keep the tab character at the start of the line. The computer needs that to understand your code. Yeah. Hey, look at you. You're waving. Hello. Why are you rotated? The robot was turned negative -0.5 radians. You need to make it upright by calling the rotate function. Rotate.
No.
0.5. Please call rotate inside the run function on line 2 and keep the tab. Boop. Character is upright. What was that?
What was what?
What did? I swear I just heard the word titty.
What?
That's what I heard.
No, you didn't.
Yeah, I did. Well, I heard that objection. We'll use code created by others like we did in the previous lesson. This time we'll solve a more complicated problem. Drawing shapes. Meet the turtle. We present you the turtle. We created the turtle to teach you how to call functions. Oh, you know what was crazy?
I'm gonna feed that turtle a straw.
I don't know why or how, but there was one viewer on yesterday's stream that watched for 3.7 hours.
What? It wasn't me leaving the stream open, I'll tell you that, because I haven't watched any of these streams. I've been here.
You haven't. I'm going to farm watch the streams. Shh, I didn't say that. To increase view counts.
Hey, speaking of view counts, the 2 most recent Ace Attorney episodes are at 15 and 17 views each.
God damn, that's more than normal, right?
Yes.
Yes. Yay. Yay.
Normally we don't even reach double digits.
Yeah. I want to work fix up your channel more when I come over tomorrow,
Yay, it's fine.
or work on it Saturday, whichever one. Wait, whichever one. Of course, after we're done with the Ace Attorney episode.
Fine.
We'll use code created by the turtle. We created the turtle to teach you how to call functions. The turtle is a little machine that moves forward, turns, and draws lines along its path. To make it draw, you give it a list of instructions. On each code line, you call one specific function. We prepared several functions for you. Move forward, pixels. Makes the turtle move forward over a given distance in pixels. Turn right, degrees. Makes the turtle turn clockwise by a precise amount of degrees. Turn left, degrees. Works the same as turn right, degrees, except the turtle turns counterclockwise. You'll use these functions the same way you used rotate before. The turtle draws a white line as it moves. We'll use this line to draw shapes. For example, to move the turtle 200 pixels, you would write move forward 200. Boop. Turning left and right. The functions turn left and turn right work the same. To turn 45 degrees to the right, you would write turn right 45. If we call turn right 45, the turtle turns 45 degrees to the right before moving on to the next instruction. Boop, boop, boop. Okay. Using these instructions, we can make any two-dimensional shape we like. Try to understand the example below. In the next practice, you'll use the functions we saw above to first draw a corner, then a rectangle like this one. Yep. In the function call below, which part is the argument? Move forward. Nope, fuck. I'm bad with names, okay? I'm bad. Draw
Bad to the bone.
Yeah.
I'm fucking stupid.
The corner is made up of two lines that are 200 pixels long. The lines are connected at each end by 9 degrees or right angle. Turn right. 90. Move forward. 200. Run. Is that correct? Is that...
No.
Yes. It was correct. Draw a rectangle with a width of 200 pixels and a height of 120. 90, 120. No. Click here, 120. That's not 120.
Yes, it is.
90. Hey. Why the fuck? 200. 90. 2, 9. 9. 2, 9. Come. Eh. Why the hell is this program so buggy? Is that right? That should be right. Cool. Write out calls to the function, move forward, and turn right to draw a rectangle with a width of 220 pixels and a height of 260 pixels. We wrote the first 2 lines for you. Be sure to write each instruction. Okay. Move forward 260. Turn right 90. Move forward 220. Turn right 90. Move forward 260. Love that. Huzzah. Alright. Coding your first function. So far we have called existing functions that the developers wrote. In this lesson we'll talk more about what functions are and see some examples. Then you will learn how to define your own functions. Functions are named sequences of instructions. Functions are sequences of instructions we give a name. We call that name an identifier. Using the identifier, we can get the computer to execute all the instructions inside the function as many times as we need. This is what a function call does. More about identifiers. I heard that.
Heard what?
Ace Attorney.
No, you didn't.
What do you mean I didn't? I
No,
totally
you
did.
didn't.
Yes, I did.
No, you didn't.
Hold it. Take that.
No.
I got video evidence of that.
No, you don't.
What do you mean? I'm streaming it and
Forged.
actively recording it right now. They're
It,
What do you mean I don't have video evidence?
it's forged.
What? No.
You edited that shit.
Well, for one, it's streaming onto YouTube, so it's actively being saved. And the stream is currently ongoing, so I can't edit it right now.
No, you edited that shit live.
No.
Yeah.
No.
Yeah.
No. If there is any code that you need to run multiple times, you can put it inside a function and give it a name. The instructions inside a function can be any code you want, and they will all run every time you call the function. Here's an example of a move and rotate function that moves the turtle forwards and then turns it 90 degrees. Move and rotate functions consist of 2 instructions, each one a separate line. Both of these instructions call another familiar function. You can write another function that calls move and rotate 4 times to draw a square of length 200 pixels. Every time we call move and rotate, the 2 functions move forward 200 and turn right 90 are called in sequence. In this simple example, it may not feel super useful. Here's a more useful and realistic one. A function to draw any square. The following function uses parameters, which we will explore in the next lesson. Drag the slider to change the square's size. 200. $100.
No.
$50.
No.
$20.
Yeah.
20 is the lowest I can go. Damn. how to define your own functions. Let's break down how you define a function. A function definition starts with the function keyword followed by a space, the function's name, parentheses, and a colon. The instructions inside the function must all start with the leading tab character. You can insert the tab character by pressing the tab key. We call those leading tabs indents. They're important to the The computer uses them to know which instructions are part of the same code block. Why do we use functions? Put a name on multiple lines of code. What? To reuse code multiple times, run multiple instructions in one go. That? Okay, just all of it. Names in code have rules. Function identifiers cannot contain spaces. In general, names in programming languages cannot contain spaces. The computer uses spaces to detect the separation between different keywords and identifiers. Instead of spaces in GDScript, we use underscores. You saw this already with functions like move forward or move local x. This is the convention we follow in GDScript. There's another convention programmers use in other programming languages. Instead of using underscores, they start words with capital letters except for the first one. With that convention, you'd write the function names like move forward or move local x. You can't pronounce that any other way. Unless I were to say m lowercase, o lowercase, v lowercase, e lowercase. No, I'm not doing that shit. No, you can't make me. Is this on? It is on, okay. There's another convention. Oh, I already got that. Identifiers also have to start with a letter or an underscore. You can't begin with a number, but you can use numbers after the first character. Which of the following names are valid function names? Not that one. Not that one. Yes. 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 Instantly moving the turtle to a different position. In order to draw multiple squares in different positions, we introduce a new function for our turtle to use. The jump function picks up the turtle and places it relative to where it is. So calling jump -100, 50, moves the turtle 100 pixels to the left and 50 pixels down without drawing any lines. Okay, draw the lines. Practice. Go to function named draw square. Yay. To draw one square of length 200 pixels, the function should take no parameters. Move forward 200. Turn right 90. And now I'm just going to copy this. Oh, allow. Oh. And now run it, and it functions. You have a function to draw one square. Draw square. Use it to draw 3 squares. Where you create a function named draw 3 squares that calls draw square 3 times. If you just call the function, all the squares will overlap to stack them diagonally. Call jump 300, 300 between 2 calls to draw square. Function. Draw 3 squares. Whoa. Crazy, huh? Draw square. Jump 300, 300. Copy. Now I don't need that jump.
Repo has an update. They added new shit.
Oh, content update?
Yeah.
Why the hell are you like
I mean, it's just cosmetics and a few changes, but it's still new shit.
That's a major update. They've been working on it for a minute. Your first function parameter in the previous lesson, you created a function to draw a square of a fixed size. This function is a bit limiting. Instead, it would be much better if we had a function to draw a square of any size, or better, any kind of rectangle. A square is a specific kind of rectangle. In previous lessons, you used the rotate function and gave it an argument. Just like rotate, we can also give our functions parameters. Parameters act as placeholders in the function's code. They work like blank spaces that get filled in each time someone calls your function. When you write a function with parameters, you create a flexible template that can work with different values each time you use it. Let's see how the rotate function is defined and uses a parameter. For now, focus on the first line, the function definition function rotate radians. The word radians is the function's parameter. It's the placeholder that gets replaced when the actual value when you call the function. When you call this function with rotate 0.5, the computer replaces the name radians in the function with 0.5. Each time you call the function, the replacement happens again. If you call rotate 1.2, radians becomes 1.2. The parameter can be filled with a number, text, or anything else in this lesson. We'll only use numbers as we have yet to learn about other value types. Incorrect, it doesn't replace the radians. It's a variable. It essentially contains that information. It's a information container. It contains that information, and when it's called, it uses that whatever it's called in will use that information that is contained within the variable. It's not replacing it, because if it replaces it, then it's just that number and it can't be called. So, unless you were to manually set it. The parameter will be filled with number. What is a function parameter? Name of a function. A number you use to make calculations. A label that you give to a value the function receives. How to create... Oh, my mother's gone. Wonder when that happened. How to create functions with parameters. When you write a function definition, the line starting with the function keyword, you can add parameters. To add a parameter with a placeholder, name inside the parentheses. When someone calls your function with a value, every copy of the parameter in the function gets replaced with that value. You can give parameters any name. How you name functions and parameters is up to you. Just remember that names cannot contain spaces. To write parameter names with multiple words in GDScript, we use underscores by convention. The following function definition is exactly equivalent to the previous one. Yep. Parameters make your code easier to reuse. You write the function once as a template, then you can call it many times with different values. Here's an example with the function to draw any square. The parameter size is a placeholder. Use a slider to change the value. When you click the button, the app calls draw square and the placeholder gets replaced with your value, drawing squares of different sizes. 200. What is the correct syntax for a function definition? Function name, parameter name. Yeah, that one. Functions have multiple parameters. A function can have multiple parameters. You can use as many placeholders as you need. To add multiple parameters, write a comma between each placeholder name. For example, function move xy has two placeholders x and y. Each one gets replaced with its own value when you call the function. Function name parameter 1, parameter 2, etc. The following example shows a function with two parameters. The function moves an entity on both x and y axes. When you call move 50, 100, every x in the function gets replaced with 50, and every y gets replaced with 100. Again, it's not replaced, it just contains the information to be called upon. When defining a function, parameters are optional. What's the correct syntax to define a function with multiple parameters? Function name, parameter 1, 2, that one. Gotta have the commas. That's a return to creative for practices, huh?
So, Lyndon, how many hours do you think we're going to have in the Apollo Justice trilogy by the time we're done?
Let's see.
because
The
we
trilogy?
have, yeah, the entire trilogy.
Okay, 5, 10,
We're currently at 76 and a half.
30. Well, by my calculations, 180.
Damn, that's a little high.
I said by my calculations. With an average stream length of 6 hours and five five cases, with an average of 2 episodes per. Um, so 6, no, 5 times 2, that's 10. Times
Really?
6 is 60. Times 3 games, that's 180.
Mm.
Yeah. Alright. Draw a corner. Before we create a rectangle of any size, let's first practice with a simpler shape. Let's call your function twice with different values. Draw a corner. Task is to add a parameter named length to your function definition. Uh, this creates a placeholder. When the app calls your function, the placeholder will get replaced with the value in parentheses. Your function should move the turtle forward by an amount defined by the length parameter, then turn right 90 degrees, and move forward by length again. Each time the app calls your function, length will be replaced with a different value. First, 240, then 120. So, length. What? Okay. That was poorly explained. Now let's make the draw corner function even more flexible. Let's add a second parameter so the angle can also vary. I will call your function with different length and angle values. Your task is to add an angle parameter after length in the function definition. Remember to separate the two placeholders with a comma. Remember, when the app calls draw corner 240, 45, the parameter length will get replaced with 240 and angle will get replaced with 45. Alright. Angle. Angle. Yep. Testing. Done. Time to write a complete function from scratch. You'll make a function that draws squares of any size. I'll call your function with different sizes. Alright. Function. Draw square. Length. And then move forward by length. No, it was turn right 90. Alright, now we can run it. Boom. Alright. Another one. Ugh. Let's create a function to draw rectangles with any length and height. I will call your function twice with different sizes. Length, height. Are you learning anything from this, Ethan? Ethan? He's probably muted or away from his... or AFK. Huzzah.
Fuck.
Welcome back.
Welcome back. I died.
You died. How'd you die?
I was playing Ultra Kill.
Ah! Introduction to member variables. In this lesson, we take
And to
a...
answer your question, fucking no, I'm not paying attention.
Hmm. You could learn shit from this.
I know I could.
Mm-hmm. Are you going to?
Probably not.
Probably not. Don't wanna deal with that shit. Introduction to member variables. In this lesson, we take a first look at variables. In games, you need to keep track of many values that change over time. The player's score, every character or enemy's health, the last checkpoint, and so much more. You need to store, retrieve, and update those values. We call those values variables. Variables are labels that you can use to keep track of values that vary over time. Here's an example of a variable tracking a character or monster's health. The line above defines a new variable named health and assigns it a starting value of 100. That's what the equal sign does. More on that below. Function parameters, which you saw in the previous lesson, are another example of variables. In this lesson, we start using variables built into Godot. They're a particular kind called member variables. Member variables are values attached to a game entity. They're useful properties like the position, rotation, and scale of a character. In a previous lesson, we saw how we could use the rotate function to rotate our character. This function increases or decreases the value of the entity's rotation member variable. So you want to reset the rotation to 0 and make the character upright using the rotate function. You can prove a rotate function can prove difficult. You need to know the character's exact current angle to cancel it out. It's much easier to use the member variable rather than the function. The following code assigns the value 0 to the character's rotation, resetting its angle and making it upright. Notice how we use the equal sign to change the value of the variable. What's a variable? A decimal number. A function that varies over time. A label that you can use to keep track of value that can change. Accessing subvariables with the dot. In video games, you will see many member variables that have subvalues. For example, the position we mentioned has two coordinates, x and y. It's the same for the scale. It has x and y subvariables. They respectively control the horizontal and vertical sides of the game entity. Who the fuck? Hi. Do I have sticky notes?
I need two.
I don't have sticky notes.
These sticky notes have lost their stick and I need them.
I don't have sticky notes.
My ball.
You left it there.
No,
Yeah, you.
it's upstairs.
No, you brought it down here. I didn't bring it down here. It was you who brought it down here.
I need sticky notes. Oh,
Go ask Mom.
Mom's not here.
Oh. Call Mom. In video games, you'll see subvariables they respectively control. To access those x and y subcomponents, you add a dot after the variable name. The dot below places the entity at 200 pixels on the axis and 250 pixels on the y-axis. Run. Since it's there, it's just there. Notice how we use the equal sign to assign the numbers on the right to this. On the right to the variable. What? On the right to the subvariables on the left. Unlike in maths, in computer programming, the equal sign does not mean is equal to. Instead, it means a sign, the result of the expression on the right to the variable on the left. We assign values so often in code that we prefer to reserve the equal sign for that. In games, the y-axis is positive going down. Note that in games, assuming your character's position starts at 0, 0. The code above moves the entity 200 pixels to the right and 250 pixels down. In math, the y-axis is generally positive going up by convention. The convention is the opposite in video games and many computer applications. The y-axis is positive going down. Why does y-axis point downwards? Blah, 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 some history bullshit. Let's look at one last example before moving on to the practice. The following code makes the character 1.5 times its starting size. Yep, it does. How do you access subvariables? The more interesting thing would be to do times equals 1.5. That way it can scale more afterwards. How do you access subvariables? Variables often hold subvalues, like the position has two subvariables, x and y. How would you access the x, for example? How do you access the x, for example? You write a slash between the variable and the subvariable name. You write an arrow between the variable and the subvariable name. You write a dot between the variable and the subvariable name. Submit. In a future lesson, we'll explain why and how those variables have subvariables. For now, just know you can use the dot to access them. We'll tell you which variables have subcomponents and what their names are. In the next lesson, you'll create your own variables and do operations on them to add blah blah blah. Blah blah blah. When are we going to get to the shit that I don't know about? Ah! Okay, goals. Draw a rectangle of 200 by 120 pixels. At the x position of 120 pixels and y position of 100 pixels. X position 120, 100, draw a rectangle 200, 120. Boom. Is that it? Yep, both checks are good. Draw 3 squares of size 100 by 100 that are 100 pixels apart on the horizontal axis. In other words, there should be a 100 pixel gap between two squares. You should draw the squares starting at the position 100, 100. This means you should position the first square at 100 on the x-axis and 100 on the y-axis. Remember, you need to use the equal sign to change the value of the variable, like the troll's position. Write your code inside the run function so the computer can recognize it. Use the provided draw rectangle function to draw each square. Alright. Position dot x equals 100. Position dot y equals 100. Draw rectangle 100, 100. Oh, draw 3 squares. Shapes are 100 pixels apart.
Dead man.
Me or you?
Me or you? Yeah.
Ah,
Anywho, I have another job interview soon-ish.
soon-ish.
Yeah.
Hmm. And by that, how many days?
2 weeks.
2 weeks.
Yeah. At fucking 11 a.m. because, yeah, of course.
11 a.m., huh?
Mm-hmm. There was not a later time available.
Hmm. Huzzah. That sounds awful. In the previous lesson, use the predefined member variable named position. In your projects, you will need to define your own variables. Imagine that you need to track the player's health in your game. You may start with 5 health points when taking a hit. The health should go down to 4 after another hit. It should be 3 and so on. To keep track of that, you can create a variable named health to which you add and subtract points. The example below introduces the print function, which outputs its argument to the output box on the left. Click the Run button to instantly run the entire function, and click the Step button to execute lines of code one by one. Debugger panel on the bottom shows the current current value of the health variable. After executing the first 2 lines of code, you will have a health variable storing a value of 4. Below we'll break down how you define new variables and explain the print function. Defining a variable. To use a variable, you must first define it so the computer registers its name. To do so, you start a line of code with the variable keyword followed by your desired variable name, like function stands for function, variable stands for variable. Variables are case sensitive, which means health and health are technically different variables. Be careful to use the same capitalization wherever you refer to the same variable, or you could be reading or writing to a different variable. The following line defines a health variable pointing to no value. You can think of it as creating a product label you have yet to stick onto something. Like the functions, a member's variable name must be unique inside a given code file. Creating 2 variables next to each other with the same name will cause an error. To use a variable, you want to assign it a starting value. You can do so using the equal sign. The code assigns its value 100 to a new variable named health. After defining your variable, you can access its value by writing the variable's name. Run. The code above will display the number 100 to some output window. Notice we don't use the variable keyword anymore, as we only need it to define a variable. Also, once you define a variable, you can change its value anytime with the equal sign. 50. About the print function. The print function is generally the first function you learn in academic programming courses. It sends prints the message or value to you give it to some output window, often a black window in plain white text. Programmers often use print to quickly check the value of their variables when their game runs. In the app, we made a special output window that captures all the print and displays a card to make it friendlier for you. Hergesbergen Company. Whoa. How long ago was that? How long ago was that? Hagaba. Hagaba. Top fans, of course. You can do it. Keep showing support to make it to the top 50. God damn it. I do want to check that though. Content. Live. I'm gonna make you a moderator. Ah ha ha. Details. I wanna. No, that's. No. How the hell do I moderate it? File name livestream.stream. That's silly. Oh, there we go. Close. Okay. Oh, chat rate. What do you mean something went wrong, YouTube? Stream health. Stream is healthy. Chat rate. Views 3. Good God. Jesus. Holy shit. 3 views. And this is only the third
Damn.
live stream. Yeah. Yeah. About the print function. Blah, blah, blah. Run. I don't know if I've read that. Here, the verb print means to send information to display screen. The function prints things on your computer display. It does not relate to printers. Variables are like labels. As we hinted above, in GDScript, variables work a bit like labels. Assigning a value to a variable is like taking your label, the variable, and sticking it onto some item, value. Like a supermarket has a database of product labels, the computer keeps a list of all variables in your code. Give them the variable name, the computer can look up the attached value. It has an important consequence. In GDScript, you can stick that label to any other value. No, wrong step. This is some text. Oop. The above code is like taking a label from the appropriate item and sticking it to the wrong thing. At line 2, the health variable holds a number. From line 3, health holds text. The computer will let you do that. The code syntax and grammar are correct, but it's not good. Variable names should describe the value they contain. So a health variable with a text value will confuse your future self and other coders. It can also cause errors in your game. Later on, we'll see how to avoid this issue with variable types. For now, let's practice creating variables. Define a variable named health with a string value of 100. Oh, string value. You said string value. Wait, starting value, not string. I can read.
Yeah, yours is a stupid one.
I'm the stupid one here. Our character in our game will have health by defining the health variable. The higher the character's health, the further away the player is from losing the game. Health that changes adds tension to the game, especially if the player is fighting with low health. It's a resource that the player should manage carefully. The character's health might get low if an enemy attacks them or they fall into a hole. We can create a function to represent damage in these cases. We pass the amount of damage from the robot should take as a parameter. Line 2 subtracts amount from health. Note the syntax which achieves this. It's a shorthand we often use. You can also use a longer form. Both of these lines have the same effect. They both subtract the value of amount from the health variable. Health minus amount. Health equals amount minus or health equals health minus amount. You may notice that the health of the robot can go below 0. We'll see how to manage this in a future lesson using conditions. The robot's health could increase instead if the player picks up an item that heals them or if they use a healing item. Heal 25. Oh, it just keeps going. Silly. Here again, the health can go beyond 100. Also, once more, the short line health plus equals amount is equivalent to the longer form health equals health plus amount. Which of these would increase the health of the robot? Select all that apply. Boop, boop, boop. Practice. In our game, the main character has a certain amount of health when it gets hit. The health should go down by a varying amount of damage. Add to the take damage function, so it subtracts the amount to the predefined health variable. The robot starts with 100 health and will take 50 damage. So health minus equals amount. Run. Huzzah. It's time to heal the robot up to full health. Write a function called heal. What? Oh, funk. Right, not just fun. What is this? Undertale? Are we having fun values here? Mount. Health. No. Plus equals amount. Run. Ah, damn. Oh. As we've seen, Godot has functions that do certain actions. For example, the show and hide functions change the visibility of things. We can also create our own functions to make custom effects like adding or removing health to a character. Godot also has special functions we can customize or add to. Take the process function. The process function gets its name because it does calculations or continuous actions. It's like a juicy. It's like a juice factory that processes juice bottles. Ugh. The bottles are always moving along a conveyor belt while different machines operate on them. It's similar in Godot, but this function can run hundreds of times a second. How many parameters does this function take? One. I wanna, damn it. The process function won't do anything until we add something to it. You might notice the underscore in front of the function name. This is a convention programmers use to coordinate work, and it'll only make sense once you have experience coding in Godot. For now, all you need to know is that if the function exists in your code and it is called precisely underscore process, then Godot will automatically run it every frame. When Godot draws on the screen, we call that a frame. Why is this underscore process function useful? It's perhaps better to see the underscore process function in action. Take the following example. Yep, false. I can't set it to false. Damn it! When you click the button Set Process True, you activate processing on the robot. From there, every frame, Godot runs the underscore process function. Since we wrote a rotate instruction, Godot is rotating the character by 0.05 radians many times a second. How often does the process function run? Once a second, multiple times a second. In the practice, you'll learn how to use the process function to rotate and move a character yourself. Nope. Okay. Make the robot rotate slowly by adding the process function. A rotation speed of about 0.05. Rotate 0.05. Run. Huzzah. What are you watching?
Aw,
Are you editing?
no.
Yeah, are you sure?
Pretty sure. I'm literally just sitting here doing nothing.
Fun. Make the robot move in a large circle slowly by rotating it, simultaneously moving it along its X direction. Ethan, would you like to learn how to code?
Uh,
What do you mean, This isn't a very hard
it
question.
means salmon.
Are you tired?
What do you think? The answer to that question is always the same.
Yes, you are. Are you more tired than usual?
Somewhat.
Somewhat. Okay. Make a robot move in a large circle
I made a
slowly.
big mistake and took a nap at like 8 yesterday, and now my sleep schedule was fucked.
Let's add the rotate and move local X functions to process. Rotate 0.05 and move underscore local underscore X by 5 pixels per frame. Run. Is it supposed to look like that? I don't know. Configure the app, report an issue. We are on lesson 11 of 27. Yay!
Bruh.
What? There's a lot. I don't want to try and get all this done
Why is
today.
there so much?
Do you not know? It's. Do you not know how much there is to programming?
I know there's a lot, but apparently all you need to make a good game is one massive fucking if statement.
Well, yeah, but I mean, you need to know um the programming language first. So I'm doing
Ah,
that. I'm learning the programming language. We've seen
what
how we can
fucking...
use our character's process function to make it move continuously. But it's not just our character that has a process function. Almost everything in the game has a process function. Dozens of times per second, Godot runs every process function in the game to update the game world. After that, it displays an image of the game world on the screen. We call that image a frame. Godot then moves on to calculate the next frame, and this happens dozens of times per second, and you get the illusion of movement. This is similar to how traditional animation works. Similar? No, that is just traditional animation. Why did he go deaf? What parameter does the process function take? Delta. Frames take varying amounts of time to calculate, depending on the game, the computer, and what the game engine needs to do. Calculate frames take more or less time to display. There will always be small variations from frame to frame. That is why the process function receives a delta parameter. Delta represents a time difference. It's the time it took Godot to complete the previous frame in seconds. We can use it to make sure the game runs at the same speed on all computers. This is because different computers have different processing power, so a fast computer will have more frames per second than a slow computer. If we ignore delta, movement speed will vary depending on the computer. Delta helps to make the game consistent for everyone. What do we know about delta? It's the time it took Godot to complete the previous frame. It's a value in seconds. It varies each frame. It does not vary. It varies each frame. Multiplying by delta. The delta you get in process is a time difference in seconds. It will generally be a tiny decimal number. To apply delta, you need to multiply your speed values by it. Process true. When multiplying by delta, you make a motion time dependent rather than frame dependent. That's essential to make your game consistent and fair. Why the time between frames matters. The time it takes to display a new frame varies. If you don't take that time into account in your code, your game will process gameplay issues and bugs. Godot provides that time to the process function through the delta parameter. In the function below, the robot moves using delta. As a result, it moves at a fixed speed. The bottom robot moves over a constant speed every frame. Without taking delta into account, it will move faster or slower than the top robot on your computer. The bottom robot will move differently for everyone. Damn. Mine's slower. Multiplying time-sensitive values by delta makes the time dependent rather than frame dependent. Thanks to that, we get reliable movement over time. Frame times vary from computer to computer and from frame to frame during gameplay. Because the frame times vary, if delta is not used, movement speed will differ for each player, making the game inconsistent and messy. What does this mean? Rotation speed times delta. We are adding rotation speed to delta. We are multiplying rotation speed by delta. We're dividing delta, we're subtracting, no, multiplying. Practice! At the moment, the rotation of the robot is frame dependent. Add delta to make the rotational speed time dependent. Times delta. Right? Yep, okay. Why did that take so long to check? In practice, make the robot move in a smooth circle using delta. The robot should rotate 2 radians per second, move 100 pixels per second forward. This combination makes it travel in a clockwise circle. Alright. Move forward. Oh. Move local x. 100 times delta. And rotate 2 times delta. Okay. I don't know why it's rotating like that. It's weird. In the above example, what does the number 4 mean? It's how fast the character rotates, it's how long the rotation takes. It's how far the character moves in pixels, it's how fast the character rotates. We can guess what a number represents by looking at the function names, but it's harder to recall what this number does by quickly looking at the code. We've seen how different functions have their own names. Using these names communicates to developers what the functions do. Hey, Mom? That's Zach. Okay. Naya wanted to show you something. Naya wanted to show you something. You should go check it out when you're ready. We can guess that what a number represents by looking at the function names, but it's hard to recall what this number does by quickly looking at the code. We've seen different functions have their own names. Using these names communicates to developers what the functions do. As we learned in Lesson 8, we can also assign labels to numbers to help us remember what they do. We call these labels variables. A variable is a label for a value we can save, change, and read later. Let's recap how to define a variable. We improved the first example to make it clear what the number 4 does. Labeling a value makes the code easier for us to read now and in the future. In the above example, which line defines the angular speed variable? Yeah. I'll be right back. Currently working.
You are?
Yeah. If you hear...
Streaming?
Yeah.
Oh. Sorry.
You're fine. It didn't take very long. Alright. If we define water. Alright, if we define variables outside of functions, we can reuse them in different functions. Because any function can use variables, we define outside of them. We call these variables script-wide. Here we use the angular speed script-wide variable in both the process function and the setAngularSpeed function. We can also define variables inside of functions. We align the variable assignment by indenting to make it part of the function body. Make sure to create the variable before using it. If we define a variable inside a function, only that function can use it. Okay. The angular speed variable only exists inside process because we defined it there. The set angular speed function can't use it. Trying to use it there will result in an error. Here's what this error might look like. Where can we define variables? Outside of functions, inside functions. Variables are also great at regrouping, or great at grouping values that control how a character behaves. Grouping them in this way allows us to easily change them. In the following practices, we'll define variables and use them with some familiar functions to make our code more readable. Alright, let's give the for here a label so we know what it does. Create a variable called angular speed outside of the process function. Make it script wide. Angular speed equals 4. Script wide. This allows us to use it in other functions too. Then replace the 4 with angular speed. Run. What? Oh. You get to set it as variable first, of course. There's something wrong with the code here. Can you see what it is? Run the code and read the error. Correct the code so it works as intended. Alright, what's the error? Angular speed equals new angular speed. Ah. Right. There we go. Easy one. Another lesson complete. In previous lessons, we decreased and increased a character's health, but there was no limit to how much health they could have. As a result, the player could increase a character's health indefinitely, which we do not want. What happens to health when we damage our character? Suppose our character has 100 health.
I think it goes down.
If we call 5 times, if it's... Well, yeah, but it was more so asking like what the result of it would be. The health would be negative 25 since the starting health is 100 and there's no limit. We probably don't want it going below 100 or below 0. We can use
Really?
conditions to run actions selectively. Conditions make your code branch into 2 paths. If the condition is met, the computer will run the corresponding instructions. Otherwise, those instructions will not run at all. Video games and other computer programs are full of conditions. For example, game input largely relies on conditions. If the player presses the button on a gamepad, the character jumps. Jump. When the computer checks a condition, this is called to evaluate a condition. All conditions evaluate to either true or false. Either the player is pressing the button or not. Either the character is touching an enemy or not. In our case, if the health goes over a maximum value, we want to reset it to the maximum. To define a condition, we use the if keyword. We write a line starting with if, type the condition, with the if type the condition to evaluate, and end the line with a colon. Notice comparison sign. Notice the comparison sign. We read the symbol as greater than. We've seen how function definitions use a colon at the end of the first line and nest content inside. In GDScript, this syntax is a recurring pattern for all code blocks. The computer knows which instructions belong to the code belong to the condition because they are indented. In the above example, we use the syntax to mean greater than. We can compare numbers in other ways too. Greater than, less than, equal to, not equal to. Here's how we might use these in if statements. If health is greater than 100, pass. If health is less than 50, pass. If health is equal to 25, pass. If health is not equal to 7, pass. Which of these statements are true? 3 is less than 1? No. 1 is not equal to 3, correct. 2 is less than 3, yes. 3 is greater than 1, yes. 2 is equal to 1, no. Or else. If the if keyword comes with a complementary else keyword, you can write an else block after an if block like so. Run. The else block will run whenever the condition above isn't met. In the following practices, we'll use conditions and improve the way our character's health changes so it has limits. The series of if statements is all wrong. Change the comparison so each comparison matches the instructions below. Keep the values and statements as they are, only change the comparison signs. As a reminder, the comparison signs are... Yep. Checks. So I just need everything to be true. If 1 is greater than health, no, it's less than. If health is equal to health, not equal to 7. Was that Minecraft? Ethan?
No.
That was the Minecraft narrator though, for when you first boot up a game version.
I didn't hear anything.
I heard press enter to activate the narrator.
I didn't hear that.
What the fuck? We have a heal function that adds an amount to the character's health. Add the function so the character's health is never greater than 80. Let's see. If health is greater than 80,
You see, I lied.
Go above 80.
But you probably already knew that.
Yeah, I did already know that, because, yeah.
Yeah. Anyway, I actually don't really know why I downloaded it since we're probably not going to ever be playing it.
Health. We have a health function that adds an amount to the character's health. The functions of the character's health is never greater than 80. I mean, if health is greater than 80, is equal to 80. Health limit is not too low. So the character's health is never greater than 80. Function that adds amount. What? You can use condition to check if the health is above 80. You need to reset the health to 80 when the health value goes above 80. Use the line if health and 80 to do this. What? Oh, fucking, I'm an idiot. Are you old though? Okay. I'll use that
Yeah.
burst later. When the robot takes damage, its health can be negative. We might want to display the health number on screen like in Japanese RPGs. We don't want negative numbers. We want to stop at 0 instead. Calling the function should reduce health by amount. If health goes below 0, set it to 0 again. Minus equals amount. If health is less than 0, health equals 0. Simple and easy. Are you planning on modding it, or?
What, Minecraft?
Yeah.
I don't know. I just have it.
Alright.
I'm not really planning on doing anything with it.
Okay. Our robot's health is always between 0 and 100, but as our robot fights, we want to increase its strength and toughness. When a character levels up, it might deal more damage to enemies, gain new abilities, or in our case, gain more health. We define a level variable to keep track of the level of the robot. It starts at level 1. When the robot has defeated enough enemies, we'll call the level up function to increment the robot's level. As we briefly saw in that last lesson, our robot could have a range of variables that could increase when it levels up. In this lesson, we'll just focus on increasing the robot's max health. The variable max health is the maximum amount the robot's health can be. We change our heal function to use this variable. We could add 5 to the max health every time the robot levels up. We would increase max health the same amount every time. If we graphed max health, it'd look something like this. Linear. The growth is linear. In our case, we want a feeling of more power and more power as the robot levels up. We want a graph like this, exponential. The growth is exponential. With each level, more max health is added than the previous level. To get the exponential growth, we multiply the max health by an amount greater than 1 each time the robot levels up. To multiply values together, we use asterisk. What is the value of damage? Level power function. Damage equals power times level. 15. We can use asterisk equals in the same way as minus equals and plus equals. What is the value of the damage now? Variable damage equals power times level. Level times 15, 30. Let's level up our robot and add exponential growth to max health. Let's move on. Let's make the robot stronger when it levels up. Add the level up function so it does the following. Increases level by 1, increases max health by 10%. Level plus equals 1. And max health times equals 1.1. Done. 121. When our robot's level is 3 or more, we want it to take a lot less damage. Add the take damage function so the following happens. If the robot's level is greater than 2, reduce the damage by 50%. If the robot's level is 3, enemy is going to attack for 10 damage. This damage should reduce to 5. If level is greater than 2, then amount Times equals 0.5. Um, oh, hmm. So damage by 50%. What? Statement. Amount
Uh,
by a value less than 1. 0.5 per. What? Huh?
I don't
Excuse
fucking
me?
know.
Damage is the correct value. You need to use an if statement at the top of the oh, at the top of the function. Oh, I need to steal it. The top of the function. Ah, ha, ha. Suppose we want to increase the size of the robot when it levels up. As you may recall, we do this by using the following code. Why do you increase in size? As we talked about in lesson 7, the scale variable has two subvariables. Oh, what? To it, x and y. This is because scale is a vector which stands for two-dimensional vector. A vector 2 represents 2D coordinates. What are vectors? A vector in physics is a quantity with a magnitude and a direction. For example, a force applied to some object, the velocity, speed, and direction of a character, and so on. We often represent this quantity with an arrow. In Godot, 2D vectors are common value type named vector 2. Unlike plain numbers, they store two decimal numbers, one for the x-coordinate and one for the y-coordinate. So far you've come across two variables in the course which are vectors. What are they? Position, scale. No, scale and position. Vectors are great for games. Vectors are essential in video games. Oh, you follow. They allow you to represent a character's movement, speed, and direction, calculate the distance to a target, and more with a little code. With little code. Take this turtle AI below. You've probably seen games where enemies move like this. This is done with just 7 lines of pure vector calculation code. This code is a bit too difficult for now, so we'll spare you the details, but this turtle gives you a glimpse of what 2D vectors can do for you and your game projects. We scale the robot again, this time by adding it directly using a vector 2. The following code has the same effect as the previous example. Yep. Notice how we can use parentheses and two arguments inside parentheses, just like other function calls. We call this a constructor function. You can think of it as a special kind of function that creates a particular type of value. The code vector 2, 0.2, 0.2, constructs a vector 2 value with its x set to 0.2 and y set to 0.2 respectively. Using vectors to change the position. We can add and subtract vectors to position because it's a vector. If we wanted to move our robot to a new relative position, we would add a vector 2 to its position. How would you move the robot 50 pixels to the left? That one. Alright. Add a line of code to the level up function to increase the scale of a robot vector by 0.2, 0.2 every time it levels up.
You're a vector.
Scale dot vector 2. No.
The fuck you mean no?
No, I was responding to what I was doing.
Mm,
Not you.
no, you were.
Scale times equals vector. Add a line to increase the scale anywhere in the level up function. Oh. Scale. After 2 levels, use a vector to increase the scale. Scale. It's not the correct scale after 2 levels? Should be 1.4, 1.4. What? Line of code to the level up function to increase the scale of a robot by vector 2. Do I just need to add it, not multiply it? Okay, I just needed to add it, not multiply it. Resetting size and position using vectors. The robot's level has increased a lot, and so has its size. Let's fix this by resetting the robot's scale and position values. Create a function named reset robot. That sets the scale and position, scale, position of the robot. The x and y subvariables of the robot's scale need to be 1.0. The robot's position needs to be vector 2. Need to be 0 and 0. Okay. Scale equals scale dot x equals 1. Scale dot y equals 1. Position equals vector 2, 0, 0. Too few arguments for reset robot. Oh. Scale dot x, scale dot y. Is that what you want? Something that is tactically invalid. Oh, that's why. Or x underscore y. What? Finally, use the function. It's fixed by resetting the robot scale and position. Create a function named that sets the scale and position of the robot. The x and y subvariables scale need to be 1. Robot's position needs to be vector 2. In the previous practice, make sure to use vectors when dealing. First line in function. Function reset. Yes, yes, I know. But explain. Need to either remove or add changes there. Don't x position y. few arguments. Expected at least 4. Underscore x. Position. Fine. I don't know what it wants. Oh, that's weird. Oh. Just reset? Okay. Scale equals vector 2 1 1 and position equals vector 2 0 0, maybe. Okay, okay. Figured it wanted some parameter. You've seen that you can use functions to reuse code. In this lesson, you'll learn about loops. Loops help you repeat code. To illustrate how loops work, let's take a game board, split it into a grid. A robot can move to neighbor cells by changing a vector to variable named cell. It represents the current cell the robot is in. When we call cell X, the robot moves to the right. Note that we delay the robot's movement in the app to help you visualize how it moves. The following code would normally move the robot instantly. We can move diagonally by adding vector 2 directly. The above code works for... Oh, okay, he left. Alright. The above code works for a predefined board with the size of vector 2, 3, 3. But the move to end function wouldn't work if the size of the board was different. The robot would either stop before the end or go too far. To implement a general solution for all board sizes, we can repeat the robot's movement until it gets to the end. For code that repeats, we can use loops. Using while loops to repeat code. You can use a while loop to make the computer repeat a block of code until you meet a specific condition or decide to break from the loop. Here's how we use a while loop. Yep. We use the variable number to keep track of how many loops the while loop completes. Each time we go through the while loop, we add 1 to number. The while loop keeps running for as long as the condition is true. In this case, it keeps running while number is less than 4. You can see that the following code is executed 4 times in the console. Run. Yep, 0, 1, 2, 3. Debarker for it. Let's apply this to our move to end function. This time we compare the number of loops to the board's width. We go through the loop until we reach the width of the board. Note that we move the robot until its position is 1 less than the board's width, because we are counting tiles from 0. A board of 3 by 3 cells would have cell coordinates going from 0 to 2 on both the x and y axes. 9. While loops can cause issues. If you're not careful, your while loop can run infinitely. In that case, the application will freeze. Take a look at this code example. Variable number equals 0, while number is less than 10, draw square. What would happen if the computer tried to run the code above? It would draw square infinitely until the program is terminated. When to use while loops. At first, you will not need while loops often. Even the code we show here has more efficient alternatives. Also, there's a safer kind of loop, for loops, which we'll look at in the next lesson. Yet, while loops have important intermediate to advanced level uses, so you at least need to know they exist and how to use them. We use while loops every time we need to loop an unknown number of times. For example, games run in a loop that typically generates 60 images per second until the user closes the game. This is possible thanks to while loops. There are other good uses for while loops. Reading and processing a file like a text document line by line, processing a constant stream of data like someone recording audio with a microphone. Reading the code and converting it into instructions the computer understands, various intermediate to advanced level algorithms, like finding paths around a map for AI. Let's practice some while loops, as they're useful to know. It's also an excellent opportunity to practice 2D vectors. Then we'll move on to the safer for loops in the following lesson. Our robot has decided to stand at the top of the board. Complete the move to bottom function so the robot moves to the bottom of the board. The board size is determined by the vector2 variable named board size. The robot's starting cell is vector2. Make sure to use a while loop so the function works for any board size. Alright. While robots. Okay, so we have, what's the variable called for the robot? What's the variable called? Ah, cell. Cell dot vector 2 is less than board size. And now it's going to be cell.y and .y. Cell.y plus equals 1. Gets to the bottom of the board. Cell.y cells make up the width. What? You have to alter the y subvariable of the cell to move the robot downwards. Yep. To move the robot, cell y needs to increase. Yep. Use while cell y is okay. I thought that might be the case, but yeah, it apparently is. All right. In the last lesson, we looked at while loops. We found they were useful if we don't know how many times we should repeat code. But while loops can result in infinite loops if we're not careful. For example, the loop below never ends because we never increment number. There's a safer and easier kind of loop, the for loop. We'll look at it in this lesson. Unlike while loops, for loops don't run forever, so you're much less to get infinite loop bugs in your game. We recommend using for loops instead of while loops because of this. In this example, I changed the code above to use for loop instead. The loop below will change the cell 3 times. Let's explain what's going on here. The range function, Godot has the helper function range, calling range n, creates a list of numbers from 0 to n minus 1. So calling range 3 outputs the list of numbers 0, 1, 2, and range 5 outputs 0, 1, 2, 3, 4. What list of numbers would range 6 create? That one. How for loops work. In a for loop, the computer takes each value inside a list, stores it in a temporary variable, and executes the code in the loop once per value. In the above example, for each item in the list 0, 1, 2, Godot sets sets number to the item, then executes the code in the for loop. We'll explain arrays more thoroughly in the next lesson, but notice that number is just a temporary variable. You create it when defining the loop, and the loop takes care of changing its value. Also, you can name this variable anything you want. This code behaves the same as the previous example run. In both examples, we print the value of the temporary variable. We created number in the first example and element in the second. As Godot moves through the loop, it assigns each value of the array to that variable. First, it sets the variable to 0, then to 1, and finally to 2. We can break down the instructions the loop runs. You can see how a loop is a shortcut to code that otherwise gets very long. We can put whatever code we like in the loop's code block, including other function calls like draw rectangle, using a for loop instead of a while loop. Here's our old move to end function, which used a while loop. If we use a for loop instead, the code becomes a little simpler. With the for loop, we check the board's width first. Then we move the robot that many times. This is simpler than checking if the robot reached the end of the board over and over. The function still works the same way. You can run it below. In the practices, we'll use for loops in different ways to get you used to using them. Once again, the robot has decided to stand at the top of the board. This time, use a for loop in the move to bottom of the board. Board size is determined by the vector2 variable named board size. The robot's starting cell is vector2 to 0. For I in range of length board size minus 1. All right, and that is going to cell y plus equals 1. But, oh, yeah. Oh, that y. Duh. Robot gets to bottom of board. Increase its cell y coordinate? Yeah, I did. I did. What? Alter the y sub variable cell to move the robot downwards. Yep. Call range of n to get a list of numbers from 0 to n minus 1. Use for number in range. Size minus 1. Okay. Okay. Yeah. Use a for loop to remove the duplicate code in the run function. Okay. That's easy. For I in range 3. Tap those. All squares are, yep. Huzzah. Lesson 18. The range function we saw in the previous lesson outputs a list of numbers. For example, calling range 3 produces the list of numbers 0, 1, 2. A list of values, numbers or otherwise, has a precise name in code. We call it an array, so we can say calling the range function produces an array of numbers. We could directly write and use that array inside our for loop instead of the range function. You can run the next function step by step to see how it works. Nah, I'm just going to run it. As you can see, the code still works the same. Notice that when we create a for loop, we also create a local variable, to which the loop assigns one value per iteration. Above, we named it number, because the array we loop over contains 3 numbers, 0, 1, and 2, but we could name it anything we like. If we unwrap the for loop above, we get the following code with the exact same behavior. The syntax of arrays. We write arrays this way in GD script, value 1, value 2, etc. You start with an opening square bracket, then you write the comma-separated values that compose the array. Finally, you need a closing square bracket to complete the array. There are a couple of valid ways. Notice how you can mix values and how they don't need to follow one another. Because arrays themselves are a value type, just like numbers or vector 2, we can assign arrays to variables to re-access them later. That'll come in handy in the next lesson, where we'll use those variables in loops. But first, let's see when you'd use an array. When you use arrays in computer programming, we use arrays all the time. Precisely, you'll use them whenever you need to store a list of things. You always need lists of things in games. The player's party in an RPG, the items in the player's inventory, the high scores in an arcade game, the objects in the game world, all of those and many more rely on arrays, using arrays to follow a path. Let's look at a widespread use of arrays in games, finding and following a path. In games, you need allies or monsters to find their way to the target, whether it's the player or some point of interest. To achieve that, we use pathfinding algorithms. As the name suggests, those algorithms find the path between 2 points and allow AIs to traverse the game. Many of those algorithms use arrays of vector 2 coordinates to represent the path. Take this turtle pet. It wants to follow the robot, but there are rocks in the way. We can tell it where to walk to reach the robot with an array. Variable path to robot, vector 1, yeah. Every value in an array is a vector and represents a cell the turtle needs to walk through. Together, all the values in the array represent a path we can draw. In upcoming lessons, you will see how we can use arrays to store player inventories or design attack combos. For now, let's practice creating arrays. The turtle wants to meet the robot, but it cannot find it on its own. Fill the turtle path array with vector 2 coordinates indicating where the turtle should move to avoid the obstacles and arrive safely to the robot. The turtle can move up, down, left, or right. It cannot move diagonally. Damn. We recommend copying and pasting to fill the array with comma-separated vector values quickly. Turtle path equals 0, 0. Turtle path equals vector 2. 1, 0. Oh, yeah. I fucking... Okay, I'm gonna copy that. And 1, 1. 5, 1. And 5, 3. What? Or a signal and you did not follow it by a name. Do I just... do that? What? Turtle path array with vector 2 coordinates indicating where the turtle should move to avoid the obstacles. And arrive safely to the robot. The turtle can move up, down, left, or right, cannot move diagonally. Recommend copying and pasting to fill the array with comma separating vector 2 values quickly. Any path that doesn't touch rocks is valid. The turtle could first move down or to the right. So the first value could either be vector 2, 1, 0 or vector 2, 0, 1. Every vector in the array should be 1 unit away from the previous one. That means there should only be a difference of 1 on the x-axis and y-axis. Okay. Two, three, 4. 2, 3, 4. And 5, 2. 1. Explain. You wrote a keyword. You wrote a function definition but forgot the parentheses. Happens in several cases. You wrote an identifier variable or function name in the wrong place. So, oh, what? Okay. Damn, that was explained poorly. Vector 2. Alright, so 1, 2, 3, 4, 5, 6, 7, 8. 3, 4, 5, 6, 7, 8, 9. 0, 0, 0, 1, 1, 1, 2, 1, 3, 1, 1, 5, 1, 5, 2, 5, 3. Okay. There we go. In this tactical game, the player and computer can select multiple units at once. You need to call the select units function and pass it an array of vector 2 coordinates to know which units to select. Each vector 2 in the array represents a cell with a unit. You can pass arrays and function calls as arguments as an array is a value type the computer recognizes. You can pass whole arrays as a single function argument. Select all units on the board by passing the correct array to the select units function. Select units. So would it be 0, 1? And of course, 1, 2, 3, 4. 5, 1. No, this one is not 0, 1. It's 1, 0. And then this one is 4, 2, 0, 3. Run. What? Arguments for select units. At most 1. Only units are selected. Gonna set that right there. Come on! Why the fuck do you do this? X paste. And that one. Alright, now that should work. All units are selected. What do you mean all What? Only units are selected. Error. Unit in cell 10 not selected. What do you mean it's not selected? What? Oh. Vector 2. 1, 0. Vector 2. 5, 1. Vector 2. 4. 4, 2. Vector 2. 0, 3. There we fucking hell. We use the range function in combination with for loops. Run. The range function produced an array that the for keyword could loop over. We can give for loops an array, and they will loop over them just the same. Instead of using the range function, we could manually write the numbers and get the same result. For each element inside the array, the for loop extracts it. It stores it in the temporary variable named number and executes the loop's code once. Inside the loop, you can access the number variable, which changes on each iteration. The code works regardless of the array or where you store it. Often you will store arrays and variables for easy access. What will this code print? Variable numbers 0, 1, 2. For number in numbers, print number 0, 1, and 2. Making the turtle walk in a loop. In the previous lesson, you made a turtle walk along a path by writing vector 2 coordinates in an array. It's a for loop that makes the turtle walk along the path. The loop works like this. For each coordinate in an array, it moves the turtle once to that cell. It's the same principle with this unit selection. For each coordinate in an array named selected units, we check if there is a unit in that cell. If so, we select it. In that case, we use an array, a loop, and a condition together. The code above uses several features you haven't learned yet. In a condition, the in keyword allows you to check if the value exists in an array. Notice the use of the period after the selected units variable to call the append function. It's because this function exists only on arrays. When functions exist only on a specific value type, you write a dot after the value to call the function on it. We'll revisit those two features again in the following lessons. The beauty of loops is that they work regardless of the size of your arrays. The code just works together, or it just works whether you have 1 or 10,000 units to select. It is all accomplished with only a couple lines of code. That's the power of computer programming. In the following practices, you will use arrays combined with for loops to achieve similar results. Our AI pathfinding algorithm provided a path for the robot to move to the right edge of the grid. Your task is to use a for loop to make the robot move. Alright. 4. For item in robot path. Cell equals item. No, I need to tab it. Declared in the current scope. What do you mean cell isn't declared in the current scope? The robot call its move to. Okay. Robot.move underscore 2. Move the robot is called move to function, like so. Robot.move to. The move to function only exists on the robot, which is why you need to access it this way. Right? And that should work. Moves along the blue path. Okay. For item in robot path, what went wrong? Int 1. Start that iterates over every cell in robot path. Okay, so since cell doesn't exist, you need to pass the cell position to the robot's move to function in the loop. Oh, robot move to. Yeah. Mm-hmm. I just forgot to put it in the here. That's what was wrong. We want to draw many rectangles, something surprisingly common in games. However, writing this code by hand can get tedious. Instead, you could store the size of your shape in arrays and use a loop to draw them all in batches. That's what you'll do in this practice. Use a for loop to draw every rectangle in the rectangle sizes array with the draw rectangle function. The rectangles shouldn't overlap or cross over each other. To avoid that, you'll need to call the jump function. Alright. For cell in rectangle sizes, draw rectangle using vector 2. Oh, no, not using vector 2, using cell. And jump. Run. For cell in rectangle sizes. I should just grab that. Because this cell, rectangle sizes, should just grab the vector. Each value in the rectangle size array is a vector 2. You'll need to access its x and y subcomponents to draw rectangles. Cell.x, cell.y. Now it should. Loop, you need to draw a rectangle and then jump, otherwise at least 2 rectangles will overlap. Going jump can be large enough to space out the rectangles. 200. Jump. 300. 0. Okay, that should work. Ah. Continue. Throughout this course, we've mostly stored numbers in variables. But what if we wanted to store a player's name? This is where strings help us. Strings are instrumental in games and applications. We can use them to display information such as the description of a spell or the name of a character. What are strings? A string is a value type which holds text to create a string. You write text wrapped in quotation marks. For example, this is a text string. The quotation marks differentiate strings from other value types and function names. You may remember we've used strings before in previous lessons. Yep. Under the hood, strings are arrays of characters. In fact, we can use a for loop to loop through the characters of a string, as we would with any other array. With which of these are strings? Why we use strings. Every piece of text you see in this app is a string that Godot is displaying for us. Much like how Vector-2 variables make calculations easier, string variables come with many helper functions and tricks we can use. We can use arrays to store strings too. This is useful for chaining animations. In this example, the play animation plays a specific animation. In the next few practices, we'll use strings in combination with different concepts from earlier lessons. Goals. Currently, the robot has a number stored in the robot name variable. Yep. Change the robot name variable so that it's a string instead. You can give it any name you'd like. Why not? Why not? In this practice, we'll chain together animations using an array of strings. You might find such combinations in fighting games. The robot has the following animation names. Jab makes the robot perform a quick punch. Uppercut, the robot uses a powerful jumping punch. Populate the combo array with animation names as strings. Then, for each animation in the array, call the play animation function to play them. The array should contain 3 values, so the robot makes these 3 attacks. 2 jabs followed by 1 uppercut. Jab. Jab. Uppercut. Oh. Combo. For I in combo. Play animation. I. Huzzah. Functions that return a value. Until now, you've learned that functions are a way to group instructions, give them a name, and reuse them. How long has this stream been going for? 4.5 hours. That's it? Okay. Functions can also make calculations and return new values. Let's look at some examples to see why this is useful. Built-in functions that return a value. Many functions built into GDScript make calculations and return a new value. For example, the round function takes a decimal number as an argument and gives you back a new whole number rounded to the nearest digit. Imagine you have a game where you track the player's health as a percentage, a decimal number going from 0 to 100. When displaying the health on the interface, you don't want to show the decimal part. In that case, you may use the round function like so. Yep. Notice how we assign the result of the function called to a variable because the round function returns a new value. We need to either store the result in a variable or use the value immediately. Above we assigned it to a variable, but you could also do the following. Set text around health. If you need to use a return value more than once, store it in a variable first. Otherwise, you can use the function call directly where you need it. A cooler example, lerp. The lerp function, shorter for linear interpolate, blends between 2 values. It takes 3 arguments, a start value, an end value, and a blend amount between 0 and 1. That controls the blend. A value 0 gives you the start value, 1 gives you the end value, and 0.5 gives you the halfway between them. gives you halfway between them. In games, lerp is often used to make things move smoothly towards a target. Note, in the code example below, I wrote the lerp function a call across multiple lines for readability. This works exactly the same as writing it on one line. Function process delta, position lerp, position get local mouse position 2 times delta. Every frame, the code calculates a position somewhere between the turtle and the mouse cursor. The lerp function takes care of everything. It's not the most robust approach for smooth movement, as you'll learn in the future, but it's a helpful function nonetheless. Writing a function that returns a value. You can make your functions return values. To make a function return a value, you use the return keyword followed by the value in question. In previous lessons, we had characters walking on grids. For those practices, you were working with cell coordinates like vector2 or vector2. But cell coordinates are not the same as positions on the screen. A cell coordinate, like vector2, tells us which cell we're in, but not where it is in pixels. To draw something on screen, we need pixel positions. We can write a function to convert cell coordinates to pixel positions. Hover over the cell below to see how it works. The yellow circle marks the pixel position at the top left corner of each cell. This corner is the reference point we use for grid position. Hover over cell to see its pixel position. 0, 0, 120, 0, 240, 0, 360, 0, and so on. And of course. To convert cell coordinates to pixel positions, we multiply the cell coordinates by the size of each cell in pixels. For example, if each cell is 120 pixels wide and tall, then cell vector 1, 0 is at pixel position vector 120, 0. Cell vector 2, 1 would be at vector 240, 120 pixels. Use the interactive grid above to visualize the calculations. This gives us the top left corner of each cell, which is the standard way to position things on a grid in games. The function below does this calculation and returns the result, so we can store it in a variable or use it right away. The return keyword sends the calculated value back to the code that called the function. Note, in Godot we write coordinates as vector2, x, y. The x value goes left to right the column, and y goes top to bottom the row. In the example below, we call the function and store the return value in the variable world position. Click the run button to see the result. Some functions return values and some do not. You can check this in the documentation panel during practices. When a practice uses specific functions, the panel shows information about them. In the documentation, functions that start with the word void do not return a value. Any other word before the function name means it returns a value of that type. You'll learn more about types in a couple of lessons. For now, let's practice returning values from functions. Sure. Complete the function that converts a cell coordinate to a pixel position on the screen. The function takes a vector2 cell coordinate as the argument, like vector2, 1. It should return the pixel position of that cell's top left corner. To convert, multiply the cell coordinate by the cell size. What are we? Convert to world coordinates. We want to apply the coordinate by cell size. Pixel position equals cell times cell size. No, of course not. Cell x times equals cell size dot x. Cell dot y times equals cell underscore size dot y. Turn cell. Okay. In previous lessons, you learned how to create arrays to store lists of values and how to loop over them. That's useful, but arrays can do much more. The real strength of GDScript arrays is that you can add and remove values from them at any time. This lets you build waiting lines of data or piles of data. We call these queues and stacks, respectively. We'll see what that means in this lesson. Let's take a look at a concrete example. Tracking orders in a restaurant management game. You're making a restaurant management game where customers place orders, and you need to handle them one by one. In the example below, customers order meals that end up in a waiting line, a queue. You need to prepare them in the kitchen. We simulate orders arriving and getting completed over time. Tomato soup, toast, burger, cheese sandwich. How do you keep track of pending and completed orders? With an array. When a customer purchases a meal, you want to add it to the array. Then, as you complete a meal in the kitchen and serve it, you want to remove it from the array. You can use the append function to add values at the end of an array to remove values from the start. You can use the pop front function. We call it pop because the value jumps out of the array. Try to read the code below before moving on. Don't worry if not everything makes sense, as we'll break it all down. Variable waiting orders, variable completed orders, function add order, meal name. Waiting orders dot append meal name. Meal name is some list. Function complete order. Variable first order equals waiting orders dot pop front. Completed orders append first order. Okay. Notice how we call some functions by writing a dot after a variable name, just like some values have variables you can access with a dot, like the x variable in position x. They can also have their own functions. Functions like append and pop front only exist on arrays. To call them, we need to write the array name, then a dot, then the function, array name dot append. Let's break down the code. We add orders to the waiting orders array by appending them. Yep. We use a string to represent a meal when calling the add order function. Add order cheese sandwich. When completing an order, we remove it from the waiting orders array by calling its pop front function. This function gives us the order back, which allows us to assign it to a temporary variable. We can then append the order to our completed orders array. When we use an array this way, we call it a queue. The first element we add to the array is the first one we remove. It's like a waiting line at a store, using arrays as stacks. Another common use of arrays is stacks of data. Take a factory management game where you need to retrieve materials from stacks of crates. They arrive at the factory piled up vertically, and you need to take them from the top. To take a crate from the back of the array, this time we use the popBack array function. This function removes pops the last value from the array and returns it to you. Here we pop the last value of the array and print what's left of the array to demonstrate how the array gets smaller. Like popFront, the function returns the value removed from the array. You will often store that value in a variable. This value could be the crate's content, which you can then use to give resources to the player. When we use an array this way, we call it a stack. This last element we add is the first one we remove. It's like a pile of plates where you take from the top. In the following practices, you will use the append, popFront, and popBack array functions. The waiting orders array will be filled over time. Your job is to move orders from the waiting list to the completed order list using the array's append and pop functions. Remember that the array's popFront function returns the popped value, which allows you to store it in a variable and then pass it to another function. Alright, so we're going to complete current order. Waiting orders. Wait, if it's that, then we don't need to have that. Job is to move orders from the waiting list to the completed orders list using the array's append and pop front functions. Or that the array's pop function returns the popped value, which allows you to store it in a variable, and then pass it to another function. Okay, so current order equals waiting orders dot pop front. And then you need to go to completed orders dot append current order. Isn't declared in the current scope. Oh, yeah, waiting orders. For I in waiting orders. And then we can set that as a variable. Run. Sometimes errors are reported outside of your code, but to view arguments. Expected at least one. For that complete current order. Order list. Order list. Wait. I could just take this. Oh, god damn it. Why does it do that? Why can't it let me click sometimes? Why? Alright, run. Why? Why? Explain. Class of errors has to do with calling functions with either the wrong number of arguments or the wrong kind of argument. To use the error message, see what's going on here. Remove, add, or change the values. Okay, what's the solution? What do you have? Okay, so don't even need that. I just need waiting orders. God fucking damn it. Why? Why? Waiting orders. Okay, run. And it should. Did it in less lines of code. Okay, crates are piling up on the platform. Move them out of the way by popping them from crates array. You need to remove them from top to bottom using the array's pop back function. Your code should remove all the crates in the array while using a while loop. Careful, if you write the program loop incorrectly, you can freeze the program. You can check if the crates array has values by writing while crates. This works because an empty array counts as false, and an array with items counts as true. While crates. Crates dot pop back. That's all I need to do. Okay. That's all. How many do we got left? It's 27. We finished 22, so we have 5 left? We have 5 left. Okay. You learn to loop over all the values in an array using the for keyword. For value in array. Print value. But what if you need to access the third item in the player's inventory? The 10th item? There's a dedicated notation to access one element in the array by index. To do so, you use square brackets with a number inside the brackets. Index 0 is the first element in the array. Index 1 is the second element in the array, and so on. You would access the fourth element in the inventory array like so. How would you access the third item in the inventory array? No, third item. Accessing the last values with negative indices. What if you want to access the last or second before last item in the inventory? In that case, you can use negative indices. If you write -1 in the brackets, you will get the last item in the array. You'll get the second to last item if you write -2. That's very convenient when you need to quickly access items from the end of the list. How would you access the third to last item in the inventory array? Third to last, that one. You can't access non-existent indices. There's a catch with this syntax. If you try to access the index that does not exist, you will get an error. You have to be careful always to access existing elements in the array. There are a couple of ways you can check for valid indices. One of them is checking the array size, checking the size of the array. Arrays come with a member function named size. You can tell it on the array anytime. You can call it on the array anytime to know its current size. Size 4. Print inventory.size. The maximum index you can access in an array is array.size. -1, it's the last item in the array. Size -1. Okay. In the following practices, you'll use array indices to realign train tracks and grab the correct item in an inventory. In our game, the player has an inventory that works as an array under the hood. The player knows they have a sword and a shield somewhere in their inventory, but they don't remember exactly where. You can see the inventory drawn on the right, along with the index of each item in the inventory. Your task is to find one sword and one shield in the array using their index. Then call use item on each of them so the player can equip those items. For example, if the first item in the array is what you need, you would call use item inventory 0. All right. Let's see. So that's the inventory. example, if the first item in the array is what you need, you would call use item. Right along with the index. All right. Variable no. For item in inventory, then jump right along with the index of each item in the inventory. I can. All right, use item in inventory 1 and use item inventory 2 and okay. Okay. We have train tracks broken down into little chunks in our game. We use them to make modular tracks and draw circuits of all shapes and sizes. However, several chunks are misaligned. You need to find them in the tracks array and pass them to the align function. To do so, you need to access the array by index. This time, though, you need to access them with negative indices. All right. Align tracks -1. Do this a couple times. 3 times. If it fucking would. Not 2. 3 and 4. Run. Huzzah. Continue. Lesson complete. Yay. We got 4 lessons left. In the last lesson, we used an array to represent a player's inventory. What time is it? 6? With just an array of item names, though, we can't easily keep track of the amount of each item. Instead, we can bundle the item names and amounts into a single dictionary. A dictionary is a data structure that allows you to map pairs of values. In the pair, we call the first value of keys as we use it to access the second. In other words, a dictionary has a list of keys, and each key points to a value. To define a dictionary, we use curly brackets. A colon separates each key and its value. A comma separates each key and value pair. Dictionaries can hold any values. Dictionaries can map about any value to any other value. For example, we can use the name of an item as a key and the amount as the corresponding value. This makes dictionaries excellent for keeping track of a player's inventory. Here we match the name, a string, to the amount, a number, but a key could be a string, a number, or even a vector. Although we can have all these different keys, keep in mind that every key has to be unique. That means we couldn't have a dictionary like the following. Variable inventory shield 5, healing heart 3, sword 1, healing heart 8. You can we could get the following error. Error duplicate key found in dictionary literal. Thought I was going to sneeze. In the above example, which key would cause an error? Healing Heart. Accessing values. We access the value of keys by writing the dictionary name with the key in between square brackets. Dictionary, key. How would you access how many gems a player has? Verbal, item count, inventory. It's gems, plural, not gem. Changing values. We can also change values directly, which is useful in our case for adding or removing items from the player's inventory. Function run inventory healing heart plus equals 1. In the following in the following practices, we'll use dictionary to create a player inventory and create a function to change the value of items. Let's give some items to the player. We use a dictionary for the player's inventory. We defined the inventory variable for you, but it contains no items. Give the player the following items by adding the correct keys and values to the dictionary. Healing Heart. Three. Gems. 9. And sword. 1. Right? That's correct. Okay, I wrote that right. I was unsure if I did. We want to change the item counts in the player's inventory whenever the player picks up or uses an item. We've started the add items function for you. The inventory dictionary should use the item name parameter as the key to access its values, and we should increase the value by amount. To test this practice, we'll use your add item function to increase the item count of healing heart, gems, and sword. Use the item name parameter as the key to access its values. We should increase the value by amount. Test this practice, we'll use add item function. Alright, so what do we do? It's inventory dictionary should use the item name parameter as the key to access its values. We should increase the value by amount. Inventory of item name plus equals amount. That should work, right? Yes. All right, we got 3 left. You can loop over dictionaries just like you learned to loop over arrays. When you loop over a dictionary, you get its key one by one. You can then use each key to get its value. Let's see how this works with 2 examples. Displaying an inventory's content. To display the player's inventory, you need to know what it contains, the name and amount of each item. To do this, you loop over the dictionary and process each key value pair one at a time. You can get a list of all the keys in a dictionary by calling the keys function. Keys function? Key. All keys per item in inventory. Keys. Oh. Print. Okay. Looping over dictionary keys is so common that GDScript gives you a shortcut. You can write the dictionary variable name directly after the in keyword in a for loop. GDScript automatically loops over the dictionary's keys. For item name in inventory, print item name. Remember, the name after the for keyword is a variable name you choose yourself. You could call it item name, item key, or anything else. This variable holds one key at a time as the loop runs. You can get each value with the syntax dictionary key as you learned in the previous lesson. So we can loop over the inventory keys, get their values, and display that information on screen. Healing Heart 3, Gems 5, Sword 1. Instead of printing the key value pairs to the output console, we can write and call a function that displays the items on the screen. Yep. Mapping a grid cells to units. You can also use a dictionary to store which units are at which positions on a game board. This is how you typically code a board game, a grid-based RPG, or a tactical RPG. So far we use string keys, but GD script dictionaries can use any type as a key. In this example, we use vector2 values as keys to represent grid positions. The only rule is that every key in a dictionary must be unique. With a for loop, you can place all the units on the board when a game starts. Okay. In the following practices, you will loop over dictionaries and process their content. We use a dictionary to store the player's inventory. The keys are item names, and the values are how many of each item the player has. Loop over the dictionary and display every item in the inventory. Call the display item function for each item. It takes two arguments, the item name and the amount. Now I want to, for item in inventory. No, I just want that. Display item item and the amount. Inventory of item. Run. Yay. We have a dictionary named units. It maps cell positions on the grid to the type of unit at that position. Use a for loop to place every unit on the game board. Call the place unit function for each unit. It takes two arguments. First the cell position, then the unit type. Okay. Dictionary maps cell positions on the grid. Use a for loop to place every unit on the game board. Position in units. We're going to place unit first the position and then units position. Basically the same thing, except the types of values are flipped. Two left. In your code, values have a particular type. You have already learned about several whole numbers, decimal numbers, streams, 2D vectors, arrays, and dictionaries. The computer uses the type of value to know which operations and functions you can use with them. As a result, it's essential to understand types. They are not fully compatible with one another, and misusing them will cause errors. A prime example. You want to display the player's health in the interface. Your code tracks health as a whole number. A value of type integer, short for integer. However, to display it on the player's screen, the computer wants text. It needs a value of type string. You can concatenate two strings with the plus operator. So the following code looks like it could work at first glance. But when running the code, we get this strange error. Invalid operand string and int operator plus. It tells you you can't add values of type string and int. They're incompatible. In that case, you need to convert health number into a string. Converting values into strings. You can get the text representation of a value calling the string function, short for string. The function returns its argument as a new string. You can use this function whenever you want to turn some number or vector into text. In this case, it turns the number 100 into the string 100, or whatever number health is currently. Converting strings into numbers. You can also convert strings into whole numbers or decimal numbers using, respectively, the int and float functions. Those functions can convert what the player writes in a text field into a number. For example, the number of potions to sell at once in a shop. Some types are partially compatible. Most types are incompatible. For example, you can't directly add or multiply an array with a number. However, some types are partially compatible. For example, you can multiply or divide a vector by a number. 10, 10. It is possible because other developers defined that operation for you under the hood. However, you cannot directly add or subtract a number to a vector. You'll get an error. That's why in earlier lessons you had to access the subvariables of position to add numbers to them. A surprising result. Take the following division, 3 divided by 2. What result would you expect to get? 1.5? 1. Well, for the computer, the result of 3 divided by 2 is 1. Wait, what? That's because for the computer, the division of two whole numbers should always result in a whole number. When you divide decimal numbers instead, you will get a decimal number as a result. Even if it's just a 0, adding a decimal place tells the computer we want decimal numbers. This shows you how mindful you need to be with types, otherwise you will get unexpected results. It can get pretty serious. Number errors can lead to bugs like controls not working as intended or charging the wrong price to players. Understanding and mastering types is a key skill for developers. Programming beginners often struggle due to the lack of understanding of types. Languages like GDScript hide the types from you by default. As a result, if you don't understand that some are incompatible, you can get stuck with facing type-related errors. You'll want to keep that in mind in your learning journey. When you write code, you will need to understand everything that's happening. That said, let's practice some type conversions. We want to display the player's energy in the user interface. Currently, our code has a type error. We're trying to display a whole number while the display energy function expects a string. Use the string function, clear the type error, and make the string amount display on the interface. You can't change the energy variable definition. Setting it to 80 would break the rest of the game's code. You must convert the value when calling display energy. String. And there we go. Now we run it. Huzzah. You complete the practice. Stay and play around or continue. Blah, blah, blah. In our game shops, we want to let the player type numbers to select the number of items they want to buy or sell. We need to know the number of items as an int, but the computer reads the player's input as a string. Your task is to convert the player's input into the numbers for the shop's code to work. Using the int function, convert the player's input into a whole number and store the result in the item count variable. Player input, get player input. Wait, what? Your task is to convert the player's input into numbers for the shop's code to work. Using the int function, convert the player's input into a whole number and store the result. Convert the player's input into a whole number, store the result in the item count variable. Okay, so we just boop. Let's get rid of that. And boop. Run. Item count matches player input. What? Get player input. Oh, shit. Item count equals int layer input. Okay. Last one. Specifying types with type hints. By default, GDScript is what we call a dynamically typed language. That means that you can just write variables, assign them a value with a number, and assign them another value with a different type. Unlike in some other languages, in GDScript, the following code is valid. Some text. But this feature often causes problems down the line. Let's take one example. Cell size, decimal number, or 2D vector. Games use grids all the time, be it for grid-based gameplay or to make algorithms faster. When working with grids, you need to convert grid coordinates into positions in the game world all the time. To do so, you give each cell a size in pixels. You'll likely pick one of two types for that, float or vector2, because pixel positions on the screen use vector2 coordinates. Either of those two values would be fine. Using a vector2 would simplify some calculations, for example, when converting grid coordinates to game world coordinates. In this example, because both cell and cell size are vector2 values, we can add them. However, if cell size is a float, we will get a type error. About operands for operator. Worse, due to dynamic typing, we won't get an error right away. We will only get the error when calling grid to world, vector 1, 1, and that's a big problem. Because we're learning, we only have small code examples in this course, but your game's code will get long and split into many files. When coding, you often forget about the code you wrote several weeks ago, and with a lot of code, it could take hours of play before players trigger a type error in your code. Using type hints. Fortunately, GDScript has optional type hints. Type hints let the computer know the value type you want for variables and report errors before running the code. To specify the type a variable can accept, you can write a colon and a type after the name when defining a new variable. You can tell the computer you want cell size only to accept vector2 variables like so. If you want to replace the cell size with a value of another type later, the computer will not let you. Parser error. The assigned value type float doesn't match the variable's type vector2. Letting the computer figure it out. GDScript comes with a feature called type inference. In many cases, but not all, the computer can figure out the type of variable for you. To do so, write colon equals without the type. The computer will set the type using the value after the equal sign. We could make cell size a variable type vector2 like so. Variable cell size colon equals vector. This takes a little typing, yet you get the benefits of using type hints like the computer reporting errors better and faster. Why bother to add hints? When you give the language hints like that, it will prevent major type errors when you work in Godot. You will see the computer can report issues as you write the code. It makes the benefit even greater. Type hints can also help improve the readability of your code. It can help to put more information directly in the code. As we saw, types are essential when coding, and when using type hints, the computer will add them to the engine's built-in code documentation system. There's an incredible third benefit for you. By using type hints, you will learn types much faster. It's excellent for learning. In the following practices, you will write the correct type hints to make the code error-free. Our variables get the correct values but not the right hints. Using the type fu, add the correct type names in variable definitions. You will write the type name between the colon and the equal sign. Note, you cannot use type inference in this practice. You need to write the type name in full. Alright, so what does it want? I literally do not know what it wants. Variable vector string. Oh. Okay. Okay. So it wants vector2. Interesting. Text. Integer. It wants this to be a string. And then this to be an integer. And this to be a float. Alright. Simple enough. Alright. It is the other way around in this practice. The type hints are fine, but the values are not. Your task is to fix the values after the equal sign, so they match the type hint of each variable. Integer. Integer. We're going to grab this, place it here. 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 Run. Alright, and that was the last one. Cool. Cool. It's been 5 hours, and this is a good stopping point. My sister wants me. I'm getting hungry. So, yeah, I think I'll stop it here. I'll add stuff to the